I have created many successful online math courses that students around the world have found invaluable. Courses in linear algebra, discrete math, and calculus. After taking this course, you will have refreshed your knowledge of machine learning for your career so that you can earn a higher salary. You will have a required prerequisite for lucrative career fields such as data science and artificial intelligence. You will be in a better position to pursue a master's or PhD degree in machine learning and data science. In this course, I cover core topics such as linear regression, linear discriminant analysis, logistic regression, artificial neural networks, and support vector machines. I will break it all down into bite-sized, no-brainer chunks. I explain each definition and go through each example step by step so that you understand each topic clearly. I will also be available to answer any questions you might have on the lecture material. Practice problems and detailed solutions are also provided to check your understanding. In this course, we will not learn any programming. We will learn the math behind machine learning and the methods of machine learning. If you're a working professional needing a refresher on machine learning or a complete beginner who needs to learn machine learning for the first time, this online course is for you. If your busy schedule doesn't allow you to go back to a traditional school, this course allows you to study on your own schedule and further your career goals without being left behind. If you plan on taking machine learning in college, this is a great way to get ahead. If you're currently struggling with machine learning or have struggled with it in the past, now is the time to master it. This course will get you started in machine learning in a smooth and natural way, preparing you for more advanced topics and dispelling the belief that machine learning is complicated, difficult, and intimidating. I want you to succeed and prosper in your career, life, and future endeavors. I am here for you. Enroll now. This is a great way to get ahead. If you're currently struggling with machine learning or have struggled with it in the past, now is the time to master it. After taking this course, you will have refreshed your knowledge of machine learning for your career so that you can earn a higher salary. You will have a required prerequisite for lucrative career fields such as data science and artificial intelligence. You will be in a better position to pursue a master's or PhD degree in machine learning and data science. Let's look at some applications of machine learning. Linear discriminant analysis can be used to solve classification problems such as spam filtering and classifying patient illnesses. Logistic regression can be used to solve binary classification problems such as determining whether a patient has a certain form of cancer or not. Artificial neural networks can be used for applications such as self-driving cars, recommender systems, online marketing, reading medical images, speech and face recognition. Real-world applications of support vector machines include classification of proteins and classification of images. In this course, I cover core topics such as linear regression, linear discriminant analysis, logistic regression, artificial neural networks, and support vector machines. I explain each definition and go through each example step by step so that you understand each topic clearly. Throughout the course, there are practice problems for you to try. Detailed solutions are provided after each problem set. Feel free to ask questions in the discussion and I will try my best to answer all of them as soon as I can. I look forward to helping you and I hope you benefit from the course. Suppose we have a set of data, x1, y1 through xn, yn. This is called the training data. Okay, now each xi here. Each xi is a vector, xi1 through xip, of measurements, where xi1 is an instance of the first input variable, x1. xi2 is an instance of the second input variable, x2, etc. Now, x1 through xp, those are called features. Or predictors. Okay, now y1 through yn. Okay, so these are little y's. Y1 through yn are instances of the output variable y, which is called the response. In linear regression, we assume that the response depends on the input variables in a linear fashion. So y equals f of x plus epsilon, where f of x is equal to beta 0 plus beta 1 x1 plus beta p xp. Okay, now here epsilon is called the error term. And beta 0 through beta p, those are called parameters. Okay, now we don't know the values of beta 0 through beta p. However, we can use the training data to approximate the values of beta 0 through beta p. Okay, so what we'll do is look at the amount by which the predictive value f of xi differs from the actual value y sub I. Okay, so we look at the amount by which f of xi differs from the actual y sub I for each of the pairs x1, y1 through xn, yn. Okay, so this is the training data. Okay, so we have y sub I minus f of xi. As the difference. We then square this and take the sum for I equals 1 through n. Okay, so we get the sum y equals 1 to n yi minus f of xi squared. Okay, so we have a sum of squares. This is called the residual sum of squares. Okay, and it's denoted RSS of beta. Like this, where beta is the column vector of beta 0, beta 1 to beta p. Okay, we want the residual sum of squares to be as small as possible. Essentially, this means that we want our predicted values, f of xi, to be as close to the actual value y sub I as possible for each of the pairs xi, yi. Now, doing this will give us a linear function of the input variables that best fits the given training data. In the case of only one input variable, we just get the best fit line. In the case of two input variables, we get the best fit plane, and so on for higher dimensions. Now, by minimizing RSS of beta, we can obtain estimates, beta 0 hat, beta 1 hat through beta p hat, of the parameters beta 0 through beta p. Okay, this method is called the least squares method. Let X be this matrix. So here we have a bunch of 1s along the first column, then x11, x21 through xn1 in the second column, and so on. And we let y be the column vector of y1 through yn. Okay, then y minus x beta is going to be equal to this minus x times the column vector of betas. Okay. And that's equal to this minus this matrix. Okay, we just multiply this matrix by this column vector. Okay, we simplify here. Okay. This is just f of x1 and so on. F of x2, f of xn. Combining, we get y1 minus f of x1 through yn minus f of xn. Okay, so y minus x beta transpose times y minus x beta, that's going to be the sum of the squares of yi minus f of xi. Okay, so we found y minus x beta here, that's equal to this. Okay, so when we take the transpose and multiply by itself, we get all these entries squared, and we sum them up. So that's what we have here. Okay, and that's just equal to the RSS of beta. Okay, therefore, the RSS of beta is y minus x beta transpose times y minus x beta. Consider the vector of partial derivatives of RSS of beta. So consider this, the derivative of RSS of beta with respect to beta 0, with respect to beta 1, and so on. Okay, now the RSS of beta is y1 minus this squared plus dot 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 plus yn minus this squared. Okay. Now let's take the derivative of that with respect to beta. Okay, so here we have a power of 2, so we drop that, multiply by the derivative of the stuff inside. Here we have the derivative is -1, since we're taking with respect to beta 0. So we multiply by -1 here. Okay, we go all the way down the line, and we get this. Now that is just equal to -2 times this row vector of 1s times y minus x beta. Okay. Let's take the derivative with respect to beta 1. Okay, so that's, once again, we drop the 2. We have the stuff inside times the derivative of the stuff inside with respect to beta 1. Here we get minus x11. Go all the way down the line, we get minus x and 1 here. But that is just equal to -2 times this row vector, x11 through xn1, times y minus x beta. Okay, so we see a pattern here. In general, the partial derivative of RSS of beta with respect to beta k is -2 times the row vector, x1k through xnk, times y minus x beta. Okay, so this column vector of the partial derivatives is equal to this. Okay, we just found this here. And that's equal to -2 times this matrix times y minus x beta. Okay. And that right here is just x transpose. So the whole thing is equal to -2 x transpose y minus x beta. If we take the second derivative of RSS of beta, say the derivative of RSS of beta, first with respect to beta k, then with respect to beta j, we get the partial derivative with respect to beta j of this here. Okay. And that's equal to 2 times x1j x1k plus dot 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 plus 2 xnj xnk. Okay. So factoring the 2 out, we get this. Now note that x equals to this matrix. Okay. So therefore, x transpose x is equal to this. Which is equal to the matrix where the jkth entry is ajk, where ajk is this. Okay, so the second derivative of RSS of beta with respect to beta k, beta j, that's equal to 2a sub jk. Okay, so the matrix of second derivatives of RSS of beta is 2x transpose x. Okay, and this matrix is called the Hessian. It's the matrix of second derivatives. Okay. Now, by the second derivative test, if the Hessian of RSS of beta at a critical point is positive definite, then RSS of beta has a local minimum there. Okay. Now, if we set our vector of derivatives to 0, we get negative 2x transpose y minus x beta equals 0. Okay. Multiplying this out, we get this. And so 2x transpose x beta is equal to 2x transpose y. Divide out the 2, we get this. Now, here we're trying to isolate beta, so take the inverse of x transpose x. Okay, we get beta equals x transpose x, the inverse of that, times x transpose y. Thus, we solved for the vector of parameters, beta 0 through beta p, which minimizes the residual sum of squares RSS of beta. So we let the approximate values beta 0 through beta p be given by x transpose x inverse x transpose y. Can arrive at the same solution for the least squares problem by using linear algebra. Let x be this matrix and y be the column vector y1 through yn as before from our training data. We want a vector beta. Okay, so let me write that here. We want a vector beta such that x beta is close to y. In other words, we want a vector beta such that the distance the distance between x beta and y is minimized. Okay. A vector beta that minimizes this distance is called a least squares solution of x beta equals to y. Okay, now note that X is an n by p plus 1 matrix. We want a beta hat in R p plus 1. Okay, we want beta hat in R p plus 1 such that X beta hat is closest to Y. Okay, note that X beta hat is a linear combination of the columns of X. Okay, so X beta hat lies in the span of the columns of X, which is a subspace of Rn denoted like this. Column space of X. Okay. So we want the vector in the column space of X that is closest to Y. The projection of Y onto the subspace column space of X is that vector. Okay, so the projection of Y onto the column space of X is going to be equal to X beta hat for some beta hat in R p plus 1. Okay. Now, the reason for that is that the projection of Y onto the column space of X is going to be a linear combination of the columns of X. Okay, so here beta hat represents the weights for that linear combination. Okay, so take a look at this graph here. This space down here, that's the column space of X. Here we have Y, the vector Y. And we're projecting that down onto the column space of X. Okay, and that's going to give us something here, X beta hat. Okay, for some beta hat. Okay, now consider Y minus X beta hat. Note that Y is equal to X beta hat plus Y minus X beta hat. Okay, here notice X beta hat just cancels out and we get Y. So that's why this is true. Okay. Now this right here, this lies in the column space of X. Okay. Now look at this. This thing here, that should be in the orthogonal complement of the column space of X. Okay, now why is that? Okay. Well, so Rn can be written, Rn can be broken into two subspaces, column space of X and the orthogonal complement of column space of X, written like this, where this is the subspace of Rn consisting of all vectors that are orthogonal to the vectors in the column space of X. Okay, now any vector in Rn can be written uniquely as z plus w, where z lies in the column space of X and w lies in the orthogonal complement of that. Now, since y lies in Rn and y equals to this, with x beta hat in the column space of X, the second vector, y minus x beta hat, that must lie in the orthogonal complement of the column space of X. So let me write that here. Okay. Okay, so now the reason why is because y is equal to something which lies in the column space of X plus something else. But that something else has to lie in the perpendicular, the orthogonal complement of the column space of X. Because any vector in Rn, okay, any vector in Rn can be written uniquely as the sum z plus w, okay, where z lies in the column space of X and w lies in the orthogonal complement. So that's what we said here. Okay. So therefore, y minus x beta hat is orthogonal to the columns of X. So if we take x transpose times y minus x beta hat, we get the zero vector. Multiply this through, we get this. Okay, now bring this over to the other side, we get this. Okay. Thus, it turns out that the set of least squares solutions of x beta equals to y consists of all and only the solutions to the matrix equation x transpose x beta equals x transpose y. Now, if x transpose x is positive definite, then the eigenvalues of x transpose x are all positive. Okay, so 0 is not an eigenvalue of X transpose X. Okay, it follows that X transpose X is invertible. Then we can solve the equation X transpose X beta hat equals to X transpose Y. We can solve that to get beta hat equals to this, which is the same result we got earlier using multivariable calculus. Let's do an example. Suppose we have the following training data. X1, Y1 is this, X2, Y2 is this, and X3, Y3 is this. Find the best fit line using the least squares method. Find the predictive value for X equals to 4. Okay, so let's form X. That's going to be this. 1, 1, 1, and 1, 2, 3. Okay, since those are the X values here, 1, 2, and 3. And form Y, that's the column vectors of all the Y values. So 1, 4, 4. Okay. Now, the coefficients, beta 0, beta 1, for the best fit line, f of x equals to beta 0 plus beta 1x, are given by this, x transpose x inverse times x transpose y. Now, x transpose is this, and therefore x transpose x is this times x. Multiply that out, we get this. Okay, so x transpose x inverse, we take the inverse of this, we get this. Okay, now x transpose x inverse times x transpose y is this times x transpose times y. Okay, multiply all of that out, we get this. Therefore, beta 0 is 0, beta 1 is 3/2. Okay, thus the best fit line is given by f of x equals 3/2 x. The predictive value for x equals to 4 is f of 4. Plug that in. And that's 6. Okay, let's look at the graph. So here are the data points, 1, 1, 2, 4, and 3, 4. This blue line is the best fit line. So the line that best fits this set of data. And the predicted value for x equals to 4 is the point corresponding to this blue line here, so that's 6. Okay, so let's review what we learned in this section. In the least squares method, we seek a linear function of the input variables that best fits the given training data. We do this by minimizing the residual sum of squares. To minimize the residual sum of squares, we apply the second derivative test from multivariable calculus. We can arrive at the same solution to the least squares problem using linear algebra. In the problem of regression, we had a set of data, x1, y1 through xn, yn, and we wanted to predict the values for the response variable y. We wanted to predict the values for the response variable y for new data points. The values that y took were numerical, quantitative values. In certain problems, the values for the response variable y that we want to predict are not quantitative but qualitative. So the values for y will take on values from a finite set of classes or categories. Problems of this sort are called classification problems. Some examples of a classification problem are classifying an email as spam or not spam, and classifying a patient's illness as one among a finite number of diseases. One method for solving a classification problem is called linear discriminant analysis. What we'll do is estimate this probability here, the probability that y is the class k, given that the input variable x is little x. Once we have all of these probabilities for a fixed little x, we pick the class k for which the probability is largest. We then classify little x as that class k. In this lecture, we'll build a formula for the posterior probability, the probability that y equals to k, given that x equals to little x. Okay, let pi sub k equal the probability that y equals to k. This is the prior probability that y equals to k. Also, let f sub k of x be the probability that x equals to x, given that y equals to k. Okay? Now, by Bayes' rule, the probability that y equals to k given x equals to little x is equal to this, the probability that x equals to x given y equals to k, times the probability that y equals to k divided by this sum. Okay, and here L ranges from 1 through big K. Okay, here we assume that little k can take on the values 1 through big K. And let me write that here. So little k can take on the values 1 through big K. Okay, these are like the classes. Okay, now note this probability here is f sub k of x. This right here is pi sub k. And And here we rewrite this as f sub L of x, and this probability here as pi sub L. That's the sum as L ranges from 1 to big K. Okay, here we just switch these around. So here I have pi k and then fk of x. Same thing in the bottom. I just switched the two terms. Okay, now we can think of the probability that y equals to k given x equals to little x as a function of little x, and denote it as p sub k of x. So p sub k of x is equal to this here. That's what we just calculated. Okay, now remember p sub k of x is the posterior probability that y equals to k, given that big X equals little x. Remember that we wanted to estimate the probability that y equals to k, given that x equals to little x, for any given little x. That is, we want an estimate for p sub k of x. Okay, remember p sub k of x is given by this. Now, if we can get estimates for pi sub k, f sub k of x, pi sub L, and f sub L of x for each L ranging from 1 through big K, then we would have an estimate for p sub k of x. Let's say that x equals x1 through xp, where x1 through xp are the input variables. So the values of x will be vectors of p elements. We will assume that the conditional distribution of x given y equals to k is the multivariate Gaussian distribution n of mu sub k sigma, where mu sub k is a class-specific mean vector and sigma is the covariance matrix of x. The class-specific mean vector, mu sub k, is given by the vector of class-specific means, mu sub k1 through mu sub kp, where mu sub kj is the class-specific mean of xj. So mu sub kj is the sum over all those I such that yi equals to k of xij times the probability that xj equals xij. Recall that xi is xi1 through xip. Okay, so for all those xi for which yi equals to k, we're taking the mean of their jth components. Sigma, the covariance matrix of x, is given by the matrix of covariances of xi and xj. So sigma is the matrix where the ijth entry, aij, is the covariance of xi and xj. And that's by definition the expectation of xi minus mu sub xi times xj minus mu sub xj. The multivariate Gaussian density is given by f of x equals to this, okay, for the multivariate Gaussian distribution n of mu sigma. Since we're assuming that the conditional distribution of x given y equals to k is the multivariate Gaussian distribution n of mu sub k sigma, we have that the probability that x equals to little x given y equals to k is equal to this. Recall that f sub k of x is the probability that x equals to x given y equals to k. So f sub k of x is equal to this right here. Recall that p sub k of x is given by this. Plugging in what we have for f sub k of x, we get this right here, okay? So this part is for f sub k, and this stuff is for f sub l. And now we can cancel out this stuff, 2 pi to the power p over 2, and the square root of the determinant of the covariance matrix sigma. Okay, cancel that out. And we get this. Note that the denominator here is equal to 2 pi to the p over 2 square root of the determinant of sigma times this sum. And also note that the sum of pi sub l f sub l of x is the same as this, just commuting the two terms. And that's equal to the probability that x equals to x given y equals to l, that's f sub l, and pi sub l is the probability that y equals to l. Now look at this sum right here. That is just equal to the probability that x equals to x. So the denominator is just 2 pi to the power p over 2 times the square root of the determinant of sigma times the probability that x equals to little x. Hence, p sub k of x is equal to this. Recall that we want to choose the class k for which the posterior probability p sub k of x is largest. Since the logarithm function is order preserving, maximizing p sub k of x is the same as maximizing the log of p sub k of x. Okay, when I say maximizing here, I mean maximizing over k. So we want the class k that gives us the maximum value for p sub k of x. Okay, let's take the log. Okay, so taking log of p sub k of x, we get log of all of this. And now breaking this up, we get log of pi sub k plus log of this minus the log of the denominator. Okay. Now that's equal to this minus log of c, where we let c be all of this stuff. So that's this. Okay. Now here we just distributed the sigma inverse here on the right hand side. Okay. And then we distributed the x and the mu sub k here. But this term x transpose sigma inverse mu sub k, that's the same as mu sub k transpose sigma inverse x. So we get two of those here. Okay, now let's see why that's true. Okay, so the claim is that x transpose sigma inverse mu sub k is the same as mu sub k transpose sigma inverse x. Let's quickly show that. Okay, so x transpose sigma inverse mu sub k, that's the same as the transpose of itself. Okay, so we get this, reversing the order and taking transpose. But now the transpose of sigma inverse is the inverse of the transpose of sigma. So that's why we have this. And sigma is symmetric, so the transpose is just itself. So we get sigma inverse. Okay, so now we have this. Okay, distributing that negative 1/2 from here. And that's how we get this. Now we just rearrange the terms here. So bring this x transpose sigma inverse mu sub k in front. Then this term plus log pi sub k and the rest. Okay, let delta sub k of x be the first three terms here. Then log of p sub k of x is delta sub k of x plus this stuff. Okay. Delta sub k of x is called it's called a linear discriminant function. Now, maximizing log of p sub k of x is the same as maximizing delta sub k of x, the linear discriminant function. Since this part here does not depend on k. Okay, so maximizing log of p sub k of x is the same as maximizing delta sub k of x. Now, if we can find estimates for pi sub k, mu sub k, and sigma, then we would have an estimate for p sub k of x, and hence for log of p sub k of x and delta sub k of x. In an attempt to maximize p sub k of x, we instead maximize the estimate of p sub k of x, which is the same as maximizing the estimate of delta sub k of x. Pi sub k can be estimated as n sub k divided by n, where n sub k is the number of training data points in class k, and n is the total number of training data points. Remember, pi sub k, okay, let me write that. Pi sub k is the probability that y equals k. We're estimating this by just taking the proportion of data points in class K. The class-specific mean vector, mu sub k, is equal to mu sub k1 through mu sub kp, where mu sub kj is the sum over all I such that yi equals to k of xij times the probability that xj is x sub ij. We can estimate mu sub kj as 1 over nk times the sum of xij, where we're ranging over all those I such that yi equals to k. So we can estimate mu sub k as this vector. Okay, now here we have 1 over n sub k. Pull that out. And we get this. Okay, now since we have a sum in each component, we can rewrite this as the sum of this vector. Okay. But that right there is just x sub I. Okay. In other words, mu sub k hat, let me write that, is equal to this. Over all I such that yi equals to k. Okay, we estimate the class-specific mean vector by the vector of averages of each component over all xi in class K. Finally, the covariance matrix sigma is estimated as 1 over n minus big K, summation k ranging from 1 to big K, sum over I such that yi equals to k of xi minus mu k hat times xi minus mu k hat transpose. Recall that delta sub k of x is given by this. So delta sub k of x, the estimate of that, is given by x transpose sigma hat inverse mu sub k hat minus 1/2 mu sub k hat transpose the inverse of sigma hat and mu sub k hat plus log of pi sub k hat. Okay, note that sigma hat, mu sub k hat, and pi sub k hat only depend on the training data and not on x. Note that x is a vector, and so x transpose sigma hat inverse mu sub k hat, that is a linear combination of the components of x. Hence, delta sub k hat of x is a linear combination of the components of x. This is why it's called a linear discriminant function. If K1, K2 is a pair of classes, we can consider whether delta sub K1 of x is greater than delta sub K2 of x. If so, we know x is not in class K2. Then we can compare delta sub K1 of x with delta sub K3 of x and rule out another class. Once we've exhausted all the classes, we'll know which class x should be assigned to. Setting delta sub K1 of x to delta sub K2 of x, we get this. And this gives us a hyperplane in RP. Okay, a hyperplane in RP. Okay, a hyperplane in, let's say, R2 is a line. A hyperplane in R3 is a plane, and so on for higher dimensions. Okay, so this equation here gives us a hyperplane in RP which separates class K1 from class K2. If we find the separating hyperplane for each pair of classes, we get something like this. Okay, so this line separates the blue from the green. Okay, this line separates the green from the orange, and this line separates the blue from the orange. Okay, so we would have three different hyperplanes. Notice that these lines don't perfectly separate the data points. So here's one blue one that's on the green side. Here's some green ones that are on the orange side. Okay. In this example, P is 2 because we have two variables, x1 and x2. And big K is 3. We have 3 classes here. Let's do an example. Suppose we have a set of data x1, y1 through x6, y6 as follows. x1 is 1, 3, x2 is 2, 3, x3 is 2, 4, x4 is 3, 1, x5 is 3, 2, and x6 is 4, 2. With y1 equals to y2 equals to y3 equals to k1, which is 1, and y4, 5, and 6 are k2, which is 2. Apply linear discriminant analysis by doing the following. A. Find estimates for the linear discriminant functions delta 1 and delta 2. Find the line that decides between the two classes. And C. Classify the new point 5, 0. If we plot the points, we get this. Okay. So here we have x1, x2, and x3, and x4, 5, and 6 here. So we expect the decision boundary to be a 45-degree line here. right? Separating the two classes. Okay, the number of features, P, is 2. The number of classes, big K, is 2. The total number of data points, big N, is 6. The number N1 of data points in class K1 is 3. And the number N2 of data points in class K2 is 3. First, we will find estimates for pi 1 and pi 2. Okay, let me write that. Pi 1 and pi 2. The prior probabilities that y equals to k1 and y equals to k2 respectively. Then we will find estimates for mu1 and mu2. The class-specific mean vectors. We can then calculate the estimate for the covariance matrix sigma. Okay. Finally, using the estimates pi 1 hat, pi 2 hat, mu 1 hat, mu 2 hat, and sigma hat. Okay, using these estimates, we can find the estimates for the linear discriminant functions, delta 1 of x, and delta 2 of x. Okay, we can find estimates for these. Okay. Pi 1 hat is given by n1 over n. So that's equal to 3 over 6. And that's 1/2. Pi 2 hat is n2 over n, so that's 3 over 6. And that's 1/2. Mu 1 hat is given by 1 over n1 sum of xi, where I ranges over all those points where yi is 1. Okay, so that's equal to 1 over 3 times, now all of those xi such that yi is 1. So those are the first 3 points, x1, x2, and x3. Okay, so we add those up, divide by 3. We get this. 5/3 and 10/3. Similarly for mu sub 2 hat, that's 1 over n2 sum of xi, where the class is 2. So those are the last 3 points. x4, x5, and x6. Okay, simplify. We get this. And sigma hat is given by 1 over n minus k, sum over k, sum over I, yi equals to k. this, plugging in the values for n and k, I get 6 and 2. Sum as k ranges from 1 to 2. And the same stuff here. Plugging in what we got for mu sub 1 hat and mu sub 2 hat, we get that sigma hat is this. Simplifying, we get this. Okay, so we have sigma hat. Now we can find the inverse. And we get this. Okay, now delta 1 hat of x is given by this formula here. So that's equal to x transpose times this. If we multiply all of that out, we get 0, 10 minus 1/2. This stuff here, you can calculate that to be 100 over 3. And pi 1 hat was 1/2. Okay. Now let's write this in terms of the components of x. So that's 0, 0x1 plus 10x2. Okay. Simplify this. Okay, this is what we get for delta 1 hat of x. Delta 2 hat of x is given by this formula. Okay, pretty much the same thing, except we have 2's everywhere here, mu sub 2 and pi sub 2. So that's x transpose times 10, 0 minus 1/2 times, okay, multiply this out. You get 100 over 3. And pi sub 2 hat was 1/2. Okay. So this becomes 10x1. Reduce this. Okay, so this is delta 2 hat of x. Now, setting delta 1 equal to delta 2, we get this equation. Okay, now these constants cancel out. So we get 10x2 equals 10x1. Divide the 10 out. We get x2 equals x1. Okay, so the line that decides between the two classes is given by x2 equals x1. Okay, let's graph that out. So here's the line, x2 equals x1. Here are the data points. And you can see that it separates them like so. Okay. Now if delta 1 hat of x is bigger than delta 2 hat of x, then we classify x as of class K1. So if x is above the line x2 equals x1, then we classify x as of class K1. Conversely, if delta 1 of x is less than delta 2 of x, then we classify x as of class K2. Okay, this corresponds to x being below the line x2 equals x1. Okay, now the point 5, 0. 5, 0 is right here. Okay, and it's below this line. So we classify it as of class K2. Okay, let's do another example. Suppose we have a set of data x1, y1 through x6, y6 as follows. x1 is 0, 2, x2 is 1, 2, x3 is 2, 0, x4 is 2, 1, x5 is 3, 3, and x6 is 4, 4. With y1 and y2 being k1, which is 1, y3 and 4 being k2, which is 2, and y5 and y6 are k3, which is 3. Apply linear discriminant analysis by doing the following. A. Find estimates for the linear discriminant functions delta 1, delta 2, and delta 3. B. Find the line that decides between each pair of classes. C. Classify the new point 1, 3. Okay, so if we graph the data points, we get this. Okay. So, as you can see, we have 3 classes here, 2 in each class. The number of features, P, is 2. The number of classes, big K, is 3. The total number of data points, N, is 6. The number N1 of data points in class K1 is 2. The number N2 of data points in class K2 is 2. And the number N3 of data points in class K3 is 2. Okay, first we will find estimates for pi 1, pi 2, and pi 3. The prior probabilities that y equals to k1, y equals to k2, and y equals to k3 respectively. So pi 1, pi 2, and pi 3. We want estimates for those. Then we will find estimates for mu1, mu2, and mu3. the class-specific mean vectors. We can then calculate the estimate for the covariance matrix sigma. Okay, finally, using the estimates, pi1 hat, pi2 hat, pi3 hat, mu1 hat, mu2 hat, mu3 hat, and sigma hat. Using these estimates, we can find the estimates for the linear discriminant functions, delta 1, delta 2, and delta 3. Okay, we can find estimates for these. Okay, so pi1 hat is given by n1 over n. So we have 2 over 6, which is 1/3. Okay, pi2 hat is n2 over n, which is the same thing, 2 over 6, which is 1/3. Pi3 hat is n3 over n, and that's 2 over 6, which is 1/3. Okay, now mu1 hat is given by 1 over n1, the sum of xi, where yi is 1. Okay, so that's 1 over 2. Now the x's that are of class 1 are the first two. So that's x1 and x2. So we get this. Mu2 hat is 1 over n2, sum of the x's where the class is 2. So that's going to be 1/2 x3 plus x4. And we get 2 1/2. Mu sub 3 hat is 1 over n3, the sum of the x's which are of class 3. And those were the last two data points, x5 and x6. Okay, so that's 7/2. 7/2. Okay, sigma hat is 1 over n minus k, the sum over k, the sum over I of this. Okay, plugging in n equals to 6 and k equals to 3, we get this. Okay, so that's 1 over 6 minus 3 times this, and that reduces to this matrix. Okay, so sigma hat inverse is this matrix. Delta 1 hat of x is given by this formula with mu1 hat and pi1 hat here. Okay, so using sigma hat and mu1 hat, we get this. If you multiply that out, get this. Multiply all this out, we get 13/2. And then pi 1 hat was 1/3. Okay, here, let's rewrite this in terms of the components of x. So that's -2 x1 plus 7 x2 and the remaining stuff. Okay, now delta 2 hat of x is given by this formula. The same thing as delta 1, except we have mu sub 2 hat and pi sub 2 hat. Okay, for this we get 7 and -2. Calculate this out. And pi 2 hat was 1/3. Okay, rewrite this in terms of the components of x. And we get this. Delta sub 3 hat of x is this. Same thing, except we have mu 3 and pi 3. Okay, for this we get 7, 7. For this we get 49/2. Pi 3 hat was 1/3. Okay, multiply this out. Okay. Now, setting delta 1 hat equal to delta 2 hat, we get this. So we get 13/2 and log of 1/3. Those cancel out. Okay. Bring this to x2 over. We get 9x2. Bring that to x1 over this side. We get 9x1. Cancel the 9s. We get x2 equals x1. Okay, so the line that decides between classes k1 and k2 is given by x2 equals x1. Okay, setting delta 1 equals delta 3, we get this. And the 13/2 and the log of 1/3, those cancel. Sorry, the log of 1/3 cancels out. And the 49/2 we can bring over here. So we get 18. And the 7x2, those cancel out. Bring the 2x1 over. We get 9x1. Okay, so divide out by the 9. We get x1 equals x1 equals to 2. So the line that decides between classes k1 and k3 is given by x1 equals to 2. Okay, now setting delta 2 equals delta 3, we get this. Okay, and now the log of 1/3 cancel out. Bring the 49/2 over here. We get 18. 7x1 cancels out. Bring the 2x2 over. Simplify. We get x2 equals 2. So the line that decides between classes K2 and K3 is given by x2 equals 2. Okay, so if we graph those lines, then we get this. Now the lines, they divide the plane into 3 regions. 1, 2, and 3. Okay, if delta 1 hat of x is bigger than delta 2 hat, that corresponds to the region above the line x2 equals x1. Okay, so that would be above this line here. Conversely, if delta 1 is less than delta 2, that corresponds to the region below the line x2 equals x1. Okay, now delta 1 hat of x greater than delta 3 hat of x, that corresponds to the region to the left of the line x1 equals 2. So that's this vertical line here. Okay. Conversely, delta 1 being less than delta 3, that corresponds to the region to the right of x1 equals to 2. Now, delta 2 hat of x greater than delta 3 hat of x. Okay, that corresponds to the region below the line x2 equals to 2. That's this horizontal line here. Conversely, delta 2 less than delta 3 corresponds to the region above the line x2 equals to 2. Okay, if delta 1 is bigger than delta 2 and delta 3, then we classify x as of class K1. So if x is in region 1, then we classify x as of class K1. Conversely, if x is in region 2, then we classify x as of class K2. And if x is in region 3, we classify x as of class K3. The point 1, 3, that's here, is in region 1, so we classify it as of class K1. In linear discriminant analysis, we find estimates p sub k hat of x for the posterior probability p sub k of x that y equals to k given that x equals to little x. We classify x according to the class k that gives the highest estimated posterior probability p sub k hat of x. maximizing the estimated posterior probability P sub k hat of x is equivalent to maximizing the log of P sub k hat of x, which in turn is equivalent to maximizing the estimated linear discriminant function delta sub k hat of x. We find estimates of the prior probability pi sub k that y equals to k, of the class-specific mean vectors mu sub k, and of the covariance matrix sigma in order to estimate the linear discriminant functions delta sub k of x. By setting delta sub k equal delta sub k prime for each pair k prime of classes, we get hyperplanes in Rp that together divide Rp into regions corresponding to the distinct classes. We classify x according to the class k for which delta sub k hat of x is largest. This lecture will look at another method for classification problems called logistic regression. Just as in linear discriminant analysis, we want to estimate the probability that y equals to k given that x equals to little x, and pick the class k for which this probability is largest. Instead of estimating this probability indirectly using Bayes' rule, as in linear discriminant analysis, we'll estimate the probability directly. Since logistic regression is more commonly used in the case of k equals to 2 classes, we will focus on that case in this lecture. We will denote the two classes by 0 and 1. An example in which logistic regression with two classes can be applied is in determining whether a patient has a certain form of cancer or not. So it's either yes or no. This lecture will provide a model for the posterior probability function. Let P of x be the probability that y equals to 1 given that x equals to little x. Okay, so this is the posterior probability. Consider P of x over 1 minus P of x. This is called the odds. Now take log of that. This is called the log odds. In logistic regression, we assume that the log odds is a linear function of the components of x. In other words, the log of P of x over 1 minus P of x is beta 0 plus beta 1 x1 plus dot 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 plus beta p xp. Okay, for some constants beta 0, beta 1 through beta p. Okay, and x is x1 through xp. So here, x1 through xp, these are the components of x. Okay, now solving for p of x, we get p of x over 1 minus p of x is e to the power of this. Okay. We just took e to the power of both sides here. So that means that p of x is e to the beta 0 through beta p xp minus p of x times that. Okay, just multiply the 1 minus p of x to both sides. Now bring this part over to the left side. We get p of x times this. Divide out by this whole thing here. Okay, so p of x is this exponential term divided by 1 plus the exponential term. Okay, this is the probability that y equals to 1 given that x equals little x. Okay, it's the probability that we want to estimate. To do this, we need estimates for the parameters beta 0 through beta p. Recall that the posterior probability function is given by this. Let's say our training data is z1, y1 through zn, yn. The y values are either 0 or 1. The probability of the observed data, okay, is given by the product of the probabilities that y equals to 1 for those zi whose y value is 1, and the probabilities that y equals to 0 for those zi whose y value is 0. That is the product, the probability that y equals to 1 given that x equals to zi, okay, for all of those I where yi equals to 1, times the product of the probabilities that y equals to 0 given that x equals to zi over all of those I such that yi equals to 0. Since the probability that y equals to 0 given x equals zi is the same as 1 minus the probability that y equals to 1 given that x equals to zi, we can rewrite the product as this. So here we have the probability that y equals to 1 given x equals to zi, and this part becomes 1 minus the probability that y equals to 1 given x equals zi. Okay, and now this we can just rewrite it as p of zi. And this part, the same thing, so we get 1 minus p of zi. Now, we want to find estimates for beta 0 through beta p that maximize the probability of our observed data given by this product here. Let L of beta 0 through beta p be the product p of zi times the product 1 minus p of zi, like this. Okay, this is called a likelihood function. Thus, to find estimates for beta 0 through beta p, we want to maximize the likelihood function. Letting beta be beta 0 through beta p, we can rewrite the likelihood function as L of beta given by this product. So here we just replaced beta 0 through beta p by beta. Recall that p of x is given by this, so p of x depends on the parameters beta 0 through beta p. Okay, to indicate this dependence, we'll write p of x semicolon beta for p of x. So L of beta is the product of p of zi semicolon beta times the product 1 minus p of zi semicolon beta. Maximizing the likelihood function is the same as maximizing the log of the likelihood function. Okay, so let capital L of beta be the log of little l of beta, which is the log of this product. Okay, this is called the the log likelihood function. We'll try to maximize the log likelihood function, capital L of beta. Note that L of beta is the sum of the log of P of Zi plus the sum of the log of 1 minus P of Zi. Okay, we just broke up the log of the product into a sum of logs. Okay, and that's equal to this, the sum of yi log of P of Zi plus 1 minus yi log of 1 minus P of Zi. Okay. Here, so when yi equals to 0, then what counts is this part. And if yi equals to 1, then what counts is this part. So that's why we can rewrite it this way. Okay, and that's equal to this. If we just combine the terms with yi in front, so we would get this. So yi times all of this. Okay. Now, look at this part here. We have log of P of Zi minus log of 1 minus P of Zi. Okay, we can rewrite this as log of P of Zi divided by 1 minus P of Zi. Okay. But note that P of Zi is e to the beta transpose Zi prime divided by 1 plus e to the beta transpose Zi prime, where Zi prime is given by this vector, 1 Zi1 through Zip. Okay, so 1 minus P of Zi is given by this, and P of Zi divided by 1 minus P of Zi is given by this. It's a simple calculation. Okay, so going back here, we can replace this part and this part. So we get this. Okay. Now, log of e to the power beta transpose Zi prime, that's just beta transpose Zi prime. Okay. And this part becomes log of 1 minus log of the denominator. So we get this here. Okay. So L of beta is given by the sum of all of this here. Okay, so we have a nice formula for the log likelihood function, L of beta. To maximize L of beta, we will use the multivariate Newton-Raphson method. Okay, let's look at how the method works, and we'll return to L of beta. This lecture, we're going to look at the multivariate Newton-Raphson method. Okay, so here's the statement of the multivariate Newton-Raphson method. Okay, suppose f from Rk to R is twice continuously differentiable. Suppose x is in Rk and is near some point A in Rk. Then the second order Taylor approximation of f of x gives f of x is approximately f of a plus the gradient of f at a transpose times x minus a plus 1/2 x minus a transpose times h times x minus a, where this is the gradient of f evaluated at a, and h is the Hessian of f evaluated at a. Now, let's say we want to maximize f. The Newton-Raphson method says to first pick an initial x value a, then consider the second order Taylor approximation of f of x for x near a. Okay. And that's given by this. Third, find the maximum of the second order approximation by taking the gradient of the second order approximation and setting it to 0. Letting q of x equal the second order approximation, which is this, we want to find the gradient of q of x and set it to 0. The gradient of q of x is the gradient of this plus the gradient of this part plus the gradient of this third part here. So that's what we have. Okay, f of a is constant, so the gradient is 0. And we have the gradient of this part, which is just the gradient of f at a. And the gradient of this part is h transpose x minus a plus h times x minus a. Now, why is that here? Okay, so let's see. You look at this part here. This is of the same form as b transpose x. So the gradient of this is just b. Okay, so we get the gradient of f of a. So this is a fact. The gradient of b transpose x is b. And we just took that fact and combined it with the multivariable chain rule. Okay, and the Jacobian of g of x given by x minus a, which is this part here, the Jacobian of that is the identity. Okay, so we're just using this fact here, except that instead of x, we have x minus a. Okay, so essentially, we're just using this fact. Okay, so that's why we have this. Now, what about this part? Okay. Well, the gradient of x transpose ax is a transpose x plus ax. Okay, notice this part here has the same form as this thing here. Okay, so we just applied this rule combined with the multivariable chain rule because we have x minus a instead of just x. Okay, so that's how we got this. Okay, so now we have the gradient of f of a, the gradient of f at a plus this stuff, and h transpose is h because the Hessian is symmetric. So we have 2h x minus a. Simplify that a bit, we get this. Setting the gradient of q of x equals to 0, we get this. Now bring the gradient of f to the other side. Get negative the gradient of f at a. Okay, get rid of that h by taking the inverse of h, multiplying both sides. So we get negative h inverse the gradient of f, assuming that h is invertible. Okay, now solving for x, bring that a over. And we get x equals a minus h inverse times the gradient of f. Thus, the maximum of q of x occurs at x equals a minus h inverse gradient of f, assuming that h is negative definite, because the Hessian of q is h transpose, which is the same as h. Okay, so if h is negative definite, then the Hessian of q is negative definite. So we get a maximum. Let x naught be a, and x sub t plus 1 be x sub t minus h inverse gradient of f at x sub t. Okay, so we got this from here, x being a minus h inverse gradient of f at a. Okay, that's what inspires this formula here. Okay. Here h is the Hessian of f evaluated at x sub t. By iteration, we get a sequence x0, x1, x2, dot, 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 which should converge to the x value that maximizes f. To summarize the multivariate Newton-Raphson method, suppose f from Rk to R is twice continuously differentiable. 1. Pick an initial value x naught equals to a. 2. Let x sub t plus 1 be x sub t minus h inverse times the gradient of f, evaluated at x sub t, where h is the Hessian of f evaluated at x sub t. Third, f attains a max at the x value to which the sequence converges. Now return to maximizing the log likelihood function, L of beta. Recall that L of beta is given by this. Note that L of beta is a real valued function of beta, where beta is given by beta 0 through beta p. Okay, so L of beta is a real value function of beta. So L is a function from Rp plus 1 to R. Further, L is twice continuously differentiable, so we can apply the multivariate Newton-Raphson method. Okay, first, pick an initial value, beta 0, given by a0, a1 through ap. 2, let beta t plus 1 be beta t minus h inverse times the gradient of L evaluated at beta t, where h is the Hessian of L evaluated at beta t. 3. L attains a max at the beta value to which the sequence beta 0, beta 1, etc. converges. To apply the Newton-Raphson method, we need to find the gradient of L and the Hessian of L. Recall that L of beta is given by this. So the gradient of L is given by the vector of partial derivatives of L. We also denote the gradient by this. Okay, so we need to know what the partial derivatives of L are. Okay, so the partial derivative of L with respect to beta j is the derivative of L of beta, which is this, and that's a sum, so we take the partial derivative of the sum, which is the sum of the partial derivatives. Okay, so we get this. Now take the partial derivative of this part, we get zij. Take the derivative of this, so we get 1 over all of that times the derivative of the stuff inside, which is this. Okay, now we have a zij here and here, so pull that out. And rewrite this part as P of Zi. Okay, so the gradient of L is given by this vector. We have the partial derivative of L with respect to beta 0. Here, the partial derivative of L with respect to beta 1, and so on. Okay, now we can pull out that summation sign, and we have the sum of these vectors here. Okay, notice that there's yi minus p of zi in every entry here. We can pull that out. And we get this. Okay. Notice this here is just zi prime, so we can rewrite it like that. Thus, the gradient of L is given by this sum here. Now for the Hessian, H, it's equal to the matrix where the tjth entry, A sub tj, is given by this. The partial derivative of L with respect to beta j, then the partial derivative of that with respect to beta t. From earlier, we know that the partial derivative of L with respect to beta j is given by this. So the partial derivative with respect to beta t of that is given by the partial derivative with respect to beta t of that sum. Okay, and this is equal to the sum of the partial derivatives of the stuff inside. Okay, Here we have a quotient, so we use the quotient rule to get this. Low d high minus high d low, all over low squared. So we get this 1 plus e to the beta transpose zi prime times the derivative of this, which is this, minus the numerator times the derivative of the denominator, which is this, all over the denominator squared. Okay, multiply this out here, distribute to each term here, and we get some cancellation. So we get this here. Notice that we have 1 plus e to the beta transpose zi prime squared here in the denominator. Let's break that apart into two pieces. Okay, so we pull out 1 over 1 plus e to the beta transpose zi prime, like this. Okay, so here we have zit. Let's bring that in front here. Rewrite this part as p of zi and this part as 1 minus p of zi. So the partial with respect to beta t of the partial with respect to beta j of L of beta is given by this. Okay, remember this is the tjth term of the Hessian. So the Hessian is given by this. Okay, zi, we have here zi prime times zi prime transpose, and that's going to give us a matrix. We can express the gradient and the Hessian in matrix notation as follows. Let y be y1 through yn. Let z be this matrix here, where the rows of z consist of the zi's. Okay. Let p be p of z1 through p of zn, and let w be this matrix, a diagonal matrix with p of z1, 1 minus p of z1, dot dot dot, p of zn, 1 minus p of zn along the diagonal. Then the gradient of L is given by this, and that's just equal to z transpose times y minus p. The Hessian is given by this formula, and we can rewrite that as negative z transpose wz. So in the Newton-Raphson method, beta of t plus 1 is equal to beta of t minus h inverse times the gradient of L evaluated at beta t, where h is the Hessian, evaluated at beta t. Okay, so we can rewrite this as what we have here, because h is given by this, and the gradient of L is given by this. Okay, where we substitute beta equals to beta t in p and w. Okay, so this simplifies to this, pulling the negative sign out. And here we have beta t. We can rewrite that part as this. So we just added the inverse of z transpose wz multiplied by itself here. So that doesn't make a difference. Okay. Now here we added w inverse. And that doesn't make a difference since that's just the identity. Also, here we regroup this part, so we have z beta t here. It's the same thing. Okay. Now we regrouped this part here, so we have w inverse times y minus p. Since we have z transpose wz inverse times z transpose w here and here, pull that out to get this. So that times z beta t plus w inverse y minus p. Okay, and we can rewrite this part as all that stuff times v, where v is the stuff inside these brackets. Okay, v is equal to z beta t plus w inverse y minus p. So we can write the iterative step in the Newton-Raphson method as beta t plus 1 equals to this, where v is equal to z beta t plus w inverse y minus p. This method is then called iterative reweighted least squares. At each iteration, beta t gets updated, and so do p, w, and v. Let's do an example. Suppose we have a set of data, z1, y1 through z5, y5, as follows. z1 is given by 1, 3, z2 is given by 2, 4, z3 is given by 4, 1, z4 is 3, 1, and z5 is 4, 2, with y1, y2, and y3 equal to k0, which is 0. Okay, so the first 3 points are of class 0. And y4 equals to y5 equals k1, which is 1. So the last 2 points are of class 1. Apply logistic regression by doing the following. A. Find the log likelihood function L of beta. B. Apply iterative reweighted least squares to find estimates for beta 0, beta 1, and beta 2. C. Find the estimated probability function p hat of x, where p of x is the probability that y equals to 1 given x equals little x. D. Classify the new point 5, 0 using the estimated probability function. Okay, so for part A, the log likelihood function L of beta is given by this. And we have 5 data points, so big N is 5. And beta is beta 0, beta 1, beta 2. Zi prime is the column vector 1, Zi1, Zi2. Okay, so we have our data points. So we have the values for the Zi prime. So just plugging that in here, okay, for each of the 5 data points, we get this. Okay. So the first 3 terms, those are for the first 3 data points. And these 2 expressions are for the last 2 data points. Now for part B. In iterative reweighted least squares, we pick an initial value beta 0 and update beta t by this formula here, where z is given by this matrix, p is given by this column vector, p of z1 through p of z5, w is given by this matrix, p of z1 times 1 minus p of z1 dot 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 p of z5 times 1 minus p of z5. It's a diagonal matrix. And v is given by this. Recall that p of zi is given by this formula. We'll pick beta 0 to be 0 as the initial value. Then p is given by this, w is this diagonal matrix, and v, if we solve for v, we'll get this. Now, using all of this, we can solve for beta 1. So beta 1 is given by this, which is approximately negative 0.69, 0.48, negative 0.48. We update p, w, v, and calculate beta 2. Okay, so beta 2 is approximately this. If we keep iterating, we get beta 3 and beta 4. Beta 5 and beta 6 are nearly the same as beta 4. Okay, so it looks like we get convergence. So beta t converges to this vector here. The estimates for beta 0, beta 1, and beta 2 are given by beta 0 hat, which is negative 1.05, beta 1 hat equals to 0.642, beta 2 hat is negative 0.642. Okay, that's what we got here from this vector. Now for part C, p hat of x is given by this, okay, where we have beta 0 hat, beta 1 hat, beta 2 hat. So we'll just plug in the values we got. Okay, p hat of x is given by this. Now for part D, p hat of 5, 0 is given by 0.8966. Since there are only 2 classes, we classify x as of class 1 if p hat of x is bigger than 1/2. Therefore, we classify 5, 0 as of class 1, okay, because this is bigger than 1/2. Note that setting beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2, setting that equal to 0 gives us a decision boundary that corresponds to the probability being 1/2. In this example, the decision boundary is given by this. And that's just the line x2 equals x1 minus 1.6. Here is what it looks like with the data points. So here's our line, x2 equals x1 minus 1.6, and our data points, the red triangles, and the 2 green squares. Okay, x2 being greater than x1 minus 1.6, that corresponds to the probability p hat of x being less than 1/2. So that's this region up here. x2 being less than x1 minus 1.6, that corresponds to the probability being greater than 1/2. So that's the region below the line. Okay, so any points here would be classified as 1, classified as of being of the class 1. Any point above this line will be classified as class 0. Let's summarize what we learned in this section. In logistic regression, we estimate the probability that y equals to k, given that x equals little x, and pick the class k for which this probability is largest. We estimate the probability that y equals to k given x equals to x directly by assuming that the log odds, log of p of x over 1 minus p of x, is a linear function of the components of x. That is, the log of p of x over 1 minus p of x is beta 0 plus beta 1 x1 plus ... plus beta p xp, where x equals x1 through xp. We find estimates for the parameters beta 0 through beta p by maximizing the log likelihood function L of beta. We maximize the log likelihood function L of beta using the method of iterative reweighted least squares. Once we have estimates beta 0 hat through beta p hat, we find the estimated probability function p hat of x. Using p hat of x, we can classify mu points. This section will look at a method for solving both regression and classification problems that uses certain compositions of linear and nonlinear functions. We construct functions involving unknown parameters that will give us the correct prediction or output value for any given input. The goal then would be to find the unknown parameters that minimize error using our training data. The functions we construct can be represented by a network diagram. Suppose x1 through xp are some input variables. We can represent these as follows: x1 through xp. Okay, we'll call these input units. Okay, and together they form the input layer. Okay, the input layer of the neural network. we include one additional input unit consisting of the constant 1. Okay, this additional input unit is called a bias unit. Now, suppose we take a linear combination of the input units. So alpha 0 times 1 plus alpha 1 x1 plus dot 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 plus alpha p xp. Okay. Letting alpha be alpha 0 through alpha p and x be 1 through 1 comma x1 through xp. Okay, we can rewrite the linear combination here. We can rewrite that as alpha transpose x. Okay, so thinking of alpha as a column vector, we take the transpose, which will give us a row vector, multiplied by x, which is a column vector. That will give us this linear combination here. Such a linear combination is called an activation. Suppose we then took h of alpha transpose x, where h is a differentiable, possibly nonlinear function. H is called an activation function. Suppose we form m such activations, ai, given by alpha I transpose x, where alpha I is this, alpha I0, alpha I1 through alpha IP, and I ranges from 1 to m. Taking h of each activation ai, we get zi, given by h of alpha I transpose x, for I equals 1 to m. We can represent the zi as follows. Okay, z1 through zm. And here, remember the alphas, those were the weights in the linear combinations that we formed to get the zi. So this line here, we'll put alpha 1, 0. So that means we're going from z1 to x0, okay, which is 1. Okay, alpha m0, we're going from zm to x0. And alpha 1, 1, we're going from z1 to x1. Alpha m1, we're going from zm to x1. And similarly for alpha 1p, we're going from z1 to xp. And alpha mp, we're going from zm to xp. Okay. The zi are called hidden units. And together they form the hidden layer of the neural network. The alpha sub ij's are called weights. Okay. Again, we include one additional hidden unit consisting of the constant 1. We could continue this process of creating more and more hidden layers, but we won't for now. Now, suppose we take a linear combination of the hidden units, okay, beta 0 times 1 plus beta 1 z1 plus dot 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 plus beta m zm, letting beta be this and z be the vector consisting of 1 z1 through zm. We can rewrite the linear combination as beta transpose z. Suppose we form k such activations, b sub k, given by beta k transpose z, where beta k is this vector and k ranges from 1 to big K. Suppose for a fixed k, little k that is, we applied some activation function g sub k to the vector of activations b1 through bk to get yk given by g sub k of b1 through bk. Suppose we have such activation functions g sub k for each k ranging from 1 to big K, and that we defined y sub k in the same way here. We can represent the y sub k as follows here. So we have y1 through yk, and similarly we draw the lines connecting the hidden units to the yi, or the y sub k. The y sub k are called output units. And together they form the output layer. The output layer of the neural network. Writing out y sub k equals g sub k of b1 through bk, more explicitly we get this, where b sub k is given by beta sub k0 plus the sum beta ki zi, as I ranges from 1 to big M. Okay, and that's equal to the sum beta ki zi as I ranges from 0 to M, if we let z0 be 1. Okay, and zi is given by h of alpha I transpose x. So this is just equal to this as long as h of alpha 0 transpose x is equal to 1. Okay, if we just let h of this alpha 0 transpose x be defined as just 1. Okay. Now, this part here is alpha 0 plus the sum alpha ij xj, j ranging from 1 to p. Okay. And we can rewrite that as just the sum as j ranges from 0 to p of alpha ij xj if we let x0 be 1. Okay, so b sub k is given by this. Okay, so b sub k can be seen as a composition of linear functions, the linear combinations, and possibly nonlinear functions in an alternating fashion. More explicitly, we're taking linear combinations of x1 through xp and of the bias unit x0 and applying the activation function h to them to get z1 to zm. We're then taking linear combinations of z1 to zm and of the bias unit z0 and applying the activation function g sub k to the collection of all of them to get y sub k. Okay, so here we have y sub k is g sub k of all of them b1 to bk, big K, where b sub little k is given by what we just found here. Okay. The network diagram we constructed has a single hidden layer, and the corresponding neural network model is called a single layer perceptron. If there are multiple hidden layers, the corresponding neural network model is called a multi-layer perceptron. If the weights and activation functions are given and we feed values in for the input units, x1 through xp, in the network diagram, we can calculate the values for the hidden units, and from there, the output units. In the diagram, we're moving from left to right, starting with the input layer, moving on to the hidden layer or hidden layers, and arriving at the output layer. Such a movement of information is called forward propagation. So, how are neural network models used to solve regression and classification problems? Depending on the type of problem, different activation functions are used. Usually, the activation function h is chosen to be the logistic sigmoid function or the hyperbolic tangent function. For a regression problem, the output unit activation function g sub k is typically chosen to be the kth projection for each k so that y sub k is equal to gk of b1 through bk, given by pi sub k of b1 through bk. So that's the kth projection, which is bk. This makes sense since b sub k is a linear combination of the zi and can potentially take on any real value. For a binary classification problem, the output unit activation function g sub k is typically chosen to be the logistic sigmoid function of the kth projection function for each k, so that y sub k is g sub k of b1 through bk is given by sigma of pi sub k of b1 through bk. Okay, pi sub k is the kth projection, so we get b sub k. And we take sigma of b sub k, where sigma of u is given by 1 over 1 plus e to the negative u. The graph of sigma looks like this. Okay, goes from 0 to 1, and we have asymptotes at 0 and 1. Okay, so y sub k given by sigma of b sub k is between 0 and 1. This makes sense for a binary classification problem. Y sub k can be interpreted as the probability that x is of class 1, and 1 minus y sub k can be interpreted as the probability that x is of class 0. For a k-class classification problem, the output unit activation function g sub k is typically chosen to be the kth projection of the softmax function, so that y sub k equals g sub k of b1 through bk is given by pi sub k of g of b1 through bk, where g of a1 through am is equal to this. Okay, g is the softmax function. Okay, so pi sub k of this is going to be e to the power b sub k over the sum of e to the bi. Okay, that's the kth projection of this. Okay. This makes sense since each y sub k, okay, given by this, is between 0 and 1, and the sum of y sub k, k ranging from 1 to bit k, is equal to 1. Y sub k can be interpreted as the probability that x is of class k. So far, we've constructed output values y sub k that depend on an input x and that involve a bunch of unknown parameters. Our goal now is to use our training data to find values for the unknown parameters that minimize error. Recall that in our network diagram, we had unknown parameters alpha ij, I ranging from 1 to m, j ranging from 0 to p, and beta sub kl, where k ranges from 1 to big K and L ranges from 0 to M. We called these weights. We'll form the vector consisting of all these weights and denote it by W. Okay, like this, W. For each type of problem, whether regression, binary classification, or multi-class classification, we're going to use a different error function. The error function e of w will turn out to be a sum of error functions e sub n of w, where n ranges from 1 to big N, and big N is the number of training points. Let the set of pairs xn, tn, k, where n ranges from 1 to big N and k ranges from 1 to big K. Let this set be the set of training data. Okay, the error function e of w will be the sum of e sub n of w as n ranges from 1 to big N, where en of w will depend on the type of problem. Let's look at regression first. The training data will consist of pairs xn, t, and k, where t and k lies in R, so t and k are real numbers, and n ranges from 1 to n, k ranges from 1 to k. In our neural network model, we're going to use y sub k to model the kth response for input x. Let f sub k of x be y sub k as defined by the neural network model with input x. We want to find the set of weights that minimizes the sum of squares error function, e of w, given by this sum here. Okay, so we take the difference, f sub k of xn minus t sub nk, okay, square that, and then we sum that over all k and n. This is analogous to minimizing the residual sum of squares in linear regression. Scaling the error function by 1/2 doesn't make a difference in the minimization. So we can write e of w like this, the sum of e sub n of w, where e sub n of w is 1/2 the sum over k of the squares of these differences. Okay, we do this for computational convenience. E of w is called the sum of squares error function. Okay, let me write that. Next, let's look at binary classification. The training data will consist of pairs xn, t, and k, where t and k lies in the set consisting of 0 and 1. So t and k could be either 0 or 1. And n ranges from 1 to big N, k ranges from 1 to big K. Let t sub k be the output variables. Let p sub k of x be the probability that t sub k equals to 1 given that x equals little x. This is the conditional probability that t sub k equals 1 given that the input variable x is equal to little x. Let n be fixed. The t sub k values are either 0 or 1. The probability of the observed data for x sub n is given by the product of the probabilities that t sub k equals to 1 for those k such that t sub nk equals to 1, and the probabilities that t sub k equals 0 for those k such that t sub nk equals 0. That is, the product, the probability that tk equals to 1, given that x equals x sub n, ranging over all those k such that t and k is 1, times the product of the probabilities that t sub k equals 0, given that x equals xn, ranging over all those k such that t and k is 0. Now, since the probability that t sub k equals to 0, given that x equals xn, is 1 minus the probability that tk equals to 1, given that x equals xn, we can rewrite the product as this. Okay, like this. And that's just equal to this, where I replaced the probability by p sub k of xn. We can rewrite this as the product like this. K ranging from 1 to big K of this stuff here. Okay. This is the probability of the observed data for a fixed xn. The probability of the observed data for all of the xn's is this product, where n ranges from 1 to big N. Okay, so we just took our product and then took the product of that as n ranges from 1 to big N. We want to maximize the probability of our observed data given by this product. In our neural network model, we're going to use the y sub k's to model the conditional probabilities p sub k of x, the p sub k of x's. Okay, so let me say that again. In our neural network model, we're going to use the y sub k's to model the conditional probabilities p sub k of x's. Okay, let f sub k of x be y sub k, as defined by the neural network model with input little x. In our product, replace p sub k of xn with f sub k of xn to get this product. Okay, this is our likelihood function. We want to find the set of weights that maximizes the likelihood function. Maximizing the likelihood function is equivalent to minimizing the negative log of the likelihood function. Taking negative log of the likelihood function, we get this. Okay, just using the properties of log, we're able to get this stuff here. So the error function E of w is the sum of E sub n of w, where E sub n of w is this here. The error function E of w given like this is called the cross-entropy error function. Next, let's look at multi-class classification. The training data will consist of pairs xn, t, and k, where t and k lie in the set consisting of 0 and 1. N ranges from 1 to n, k ranges from 1 to k. Let t sub k be the output variables. Let p sub k of x be the conditional probability that t sub k is 1, given that the input x is little x. Let n be fixed. The t sub k values are either 0 or 1. Only one of the t sub k values is 1, and the rest are 0. The probability of the observed data for x sub n is given by the probability that t sub k equals to 1 for that k such that t sub nk equals 1. That is the probability that t sub k equals 1 given that x equals xn. We can rewrite this as p sub k of xn equals the product of p sub k of xn to the power t and k. Okay, since t and k will be 1 for the case that the index is k and 0 otherwise. This is the probability of the observed data for a fixed x sub n. The probability of the observed data for all of the xn's is this product as n goes from 1 to big N. Okay, we want to maximize the probability of our observed data given by this product. In our neural network model, we're going to use the y sub k's to model the conditional probabilities p sub k of x's. Let f sub k of x be y sub k, as defined by the neural network model with input little x. In our product, replace p sub k of xn with f sub k of xn, okay, to get this product. This is our likelihood function. We want to find the set of weights that maximizes the likelihood function. Maximizing the likelihood function is equivalent to minimizing the negative log of the likelihood function. Taking negative log of the likelihood function, we get this. So the error function E of W is equal to the sum of E sub n of W, where E sub n of W is this. Okay, the error function E of W, given like this, is called the multi-class cross-entropy error function. So far, we've seen that for each type of problem, there is a corresponding error function E of W. The method we use to minimize E of W is gradient descent. Gradient descent is an iterative process where we start with an initial value for W and update W as follows. Okay, W tau plus 1 is W tau minus eta times the gradient of E at W tau. Eta is called the learning rate. In the process of updating W, we need to find the gradient of the error function. E of W is a function of all the individual weights. Let W sub ji denote the weight of the connection that goes from unit I to unit j, where unit I is the ith unit in some layer, and unit j is the jth unit in the next layer. The gradient of E of W is the vector consisting of all the partial derivatives, partial of E with respect to W sub ji. Since E of W is the sum of E sub n of w, where n ranges from 1 to big N. The partial derivative of E with respect to wji is the sum of the partial derivatives of En with respect to wji. So we just need to calculate the partial derivative of E sub n of w with respect to wji. Suppose L is a non-biased unit in the same layer as unit J. Recall that there is an activation, A sub L, corresponding to unit L, which is a linear combination of all of the units in the previous layer. Note that E sub n of w can be seen as a function of the activations A sub L. By the multivariable chain rule, the partial derivative of En with respect to wji is the sum of the partial derivative of En with respect to Al times the partial derivative of Al with respect to wji, summing that over L, where L runs over all non-biased units in the same layer as unit J. However, A sub L doesn't depend on W sub Ji unless L equals to J. So the partial derivative of A sub L with respect to Wji is 0 for all L not equal to J. That means the partial derivative of En with respect to Wji is the sum of the partial derivative of En with respect to Al times the partial of Al with respect to Wji. The sum of that over L. So what we have here is that all these terms are 0 except when L is J. So we just get one term here where we have AJ here. Now, A sub J is a sum of W sub JS times ZS over S, where S runs over all units in the layer previous to the layer for unit J. And ZS is the value for unit S. So when we take the partial derivative of A sub J with respect to W sub Ji, all these terms are 0. The partial derivatives are all 0 except when S is I. So the partial derivative of A sub J with respect to W sub Ji is just Zi. Thus, the partial derivative of En with respect to Wji is the partial of En with respect to Aj times Zi. Let delta sub j be the partial of En with respect to Aj. Then the partial of En with respect to Wji is delta j times Zi. We just showed that the partial derivative of En with respect to Wji is delta j times Zi, where delta j is the partial of En with respect to Aj. It remains for us to find delta j. If j is an output unit k, then it can be shown that delta k is f sub k of xn minus t sub nk. Otherwise, j is a hidden unit, like this. Note that we can view E sub n of w as a function of the activations A sub k corresponding to the non-biased units k in the layer after the layer for unit j. By the multivariable chain rule, delta j, which is given by the partial of En with respect to aj, is equal to the sum over k of the partial of En with respect to ak times the partial of ak with respect to aj, where k runs over all non-biased units in the layer after the layer for unit j. Okay, so it looks something like this. So here's unit j, and here are the units k and k prime in the layer after the layer for unit j. Now a sub k is the sum of wkt times h of at, where t runs over all units in the layer for unit j, and h is some activation function. Okay, so when we take the partial derivative of a sub k with respect to a sub j, none of these terms count except when t is j. So the partial of a sub k with respect to aj is wkj h prime of aj. Letting delta k be the partial of En with respect to ak, delta j is the sum of delta k times wkj h prime of aj. And we can pull that h prime of aj out, doesn't depend on k, and we have wkj delta k. So delta j is determined by the delta k's for all those units k for which there is a connection that goes from unit j to unit k. The equations delta j equals to this are called backpropagation equations. So here's a diagram with unit j and units k and k prime in the layer after the layer for j. So wkj is the connection going from j to k, and we have wk prime j going from j to k prime. Okay, information is propagated backwards from the units k to unit j, so to speak. To summarize, the partial derivative of E of w with respect to wji is the sum of the partials of En with respect to wji, where the partial of En with respect to wji is delta j zi, and delta k is given by this if k is an output unit. Delta j is given by this if j is a hidden unit. Okay, so let's look at the diagram here. We could find the delta k's for all the output units k, then plug those into the backpropagation equations to find the delta j's for all the hidden units j in the layer right before the output layer. Then use these delta j's to find the deltas in the next layer down, continuing in this way until we find all the deltas. This process of finding the gradient of E is called backpropagation. Let's summarize what we learned in this section. We began by using a neural network diagram to construct output functions f sub k of x for each output unit k. We used weights and activation functions to construct the output functions. We then used the training data and a chosen error function e of w to find values for the weights. We did this by minimizing the error function. For regression problems, we used the sum of squares error function along with the output activation function g sub k of b1 through bk equals bk, or b sub k. For binary classification problems, we used the cross-entropy error function along with the output activation function given by this, sigma of b sub k, where sigma is the logistic sigmoid function. For multi-class classification problems, we used the multi-class cross-entropy error function, along with the output activation function g sub k of b1 through bk given by this, where g sub k is pi k composed with g, and g is the softmax function. To minimize the error function e of w, we used gradient descent, which required finding the gradient of e at w tau. To find the gradient of e at w tau, we used backpropagation. This section and in the next two sections, we will look at some further methods for solving classification problems. We will look at the maximal margin classifier, the support vector classifier, and the support vector machine. We will focus on the case of two classes labeled 1 and -1. Suppose x1, y1 through xn, yn are our training data points. Each xi is a p-dimensional vector, xi1 through xip, and y sub I lies in the set containing -1 and 1. So the y's are either 1 or -1. For instance, if p equals to 2, the xi are points in the two-dimensional plane. If we plot the points xi, we might have something like this. Okay, the circles indicate class 1, and the x's indicate class -1. In this example, the points appear to be separable by a line. So maybe something like this. If the xi's are separable like this by a line when p equals to 2, or by a hyperplane more generally, then we can use such a line to separate the two classes and classify any new point depending on which side of the line the point falls on. The maximal margin classifier is used in this case. If the xi's can't be separated by a line or hyperplane, we can still try to separate the two classes with a line or hyperplane using the support vector classifier. Finally, if we want a nonlinear decision boundary separating the two classes, we can use the support vector machine. First, let's start with the maximal margin classifier. We want to define what a hyperplane is. The xi's lie in Rp, a p-dimensional vector space. A hyperplane in Rp, for some constants beta 0 through beta p, is the set of points x1 through xp such that this equation holds. if p equals to 2, a hyperplane in R2 is a line. If p equals to 3, a hyperplane in R3 is a plane. Let's say that our xi's are separable by a hyperplane. For instance, like this. Now, note that there are multiple hyperplanes that separate our points. So here we have the blue line and also the orange line. They both separate the points. We want to choose our hyperplane such that the hyperplane is as far from each point as possible. Okay, let's make this more precise. A hyperplane, beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0, is said to be a separating hyperplane just in case beta 0 plus beta 1 xi1 plus dot 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 plus beta p xip is greater than 0 if y sub I is 1, and it's negative if y sub I is negative 1. Okay. In other words, yi times this expression is positive for each I as I ranges from 1 to big N. Okay. It can be shown that the perpendicular distance between xi and the separating hyperplane beta 0 plus dot 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 plus beta p xp equals to 0 is given by this expression here. Okay, so let me write that. So let's say we have a point xi, and we have a separating hyperplane beta 0 plus beta 1 x1 plus beta p xp equals to 0. Okay, this is the separating hyperplane. The perpendicular distance between xi and this plane, this hyperplane, is given by this expression. Okay. And here we have 1 over the norm of beta, where beta is beta 1 through beta p. So this beta is not including beta 0. Okay, so the proof of this claim that the perpendicular distance between xi and this separating hyperplane is equal to this expression, okay? The proof of that you can find in an optional video or document titled Proof 1. For a fixed separating hyperplane, beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0. Okay, for a fixed separating hyperplane like this, consider the minimum distance between the xi's and the separating hyperplane. In other words, consider the minimum of 1 over the norm of beta yi times beta 0 plus dot 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 plus beta p xip as I ranges from 1 to n. Okay, so take the smallest of these distances. This is the distance between the hyperplane and the xi closest to the hyperplane. It's called the margin of the hyperplane. Okay, the margin of the hyperplane. the margin is the smallest of these distances. In this video, we're going to show that the perpendicular distance between xi and the separating hyperplane beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0 is given by this expression here. Let's look at the proof. The hyperplane given by this can be rewritten as this. Just subtract beta 0 from both sides. Okay, so we can see what the normal vector will be here. Okay, the normal vector is n given by beta 1 to beta p divided by the norm of beta. Let L denote the hyperplane, so this line here. And here we have n, the normal vector to L. Okay, so it's perpendicular to L. Let x naught be the vector where L and the normal line intersect. Let x be an arbitrary point. Okay, draw the line U, here the orthogonal projection of x onto L. Let Z be the line going from x0 to x. And let V be the line perpendicular to L that goes from here to x. Note that Z is x minus x naught. Also, U plus V is Z. And note also that n dot U is 0. Okay, n is perpendicular to U. Okay, so n dot Z minus V is 0 because U is Z minus V here. But Z is x minus x naught, so replace that here. Okay, and V is equal to k times n for some scalar k. Okay, because V here is parallel to n. Okay, take the dot product of n with the stuff inside here. So n dot x minus x0 minus k times n dot n. Okay, but n dot n is just 1, so we get k. Solving for k, we get n dot x minus x0. As you can see from the graph, the distance between x and L is the norm of V. Okay, so the norm of V, which is the absolute value of k times the norm of n, which is the absolute value of k. So the norm of V is the absolute value of k, which we found to be this. So that's the absolute value of this. Okay, distributing the n, we get n dot x minus n dot x naught. And that's equal to negative beta naught over the norm of beta. Okay, let's see why. We have that x naught lies on L. So x naught satisfies this equation. Okay, but this part here is just the norm of beta n dot x naught. Okay, so solving for n dot x naught, I get negative beta naught over the norm of beta. Okay, so we can just replace this with this. Okay, simplifying, we get positive beta naught over norm of beta. Therefore, the perpendicular distance between xi and the hyperplane is given by the absolute value of this. n dot xi is given by this, because n is just 1 over the norm of beta times beta 1 to beta p, and we're just taking the dot product. Okay, adding the numerators, we get this. And pulling that norm of beta out, we get this. And that's equal to 1 over the norm of beta times this, if this expression is positive, and it's equal to 1 over the norm of beta times negative this expression, if that expression is negative. Okay, and this is equal to this piecewise defined expression. So if yi is 1, then we get this expression. If yi is negative 1, we get negative times that expression. Okay, the reason is if yi is 1, then this expression is positive, so we get this. If yi is negative 1, then this expression is negative, and we get this. Okay, so that's just equal to 1 over the norm of beta times yi times this expression. Hence, the perpendicular distance between xi and the separating hyperplane, beta 0 plus beta 1 x1 plus dot 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 plus beta p xp equals to 0, is given by this expression. We want to choose the separating hyperplane that maximizes the margin of the hyperplane. In other words, we want to choose beta 0, beta 1 through beta p such that the margin is maximal. So we have the following problem. Maximize this expression here. This is the margin, okay, where beta 0, beta 1 through beta p lies in S, and S is this set, the set of all vectors beta 0 through beta p in R p plus 1, such that this expression is greater than 0 for all I, as I ranges from 1 to n. Okay, so you can think of this set S as consisting of those hyperplanes that separate our data points. Okay, so we want that hyperplane that maximizes the margin. S should actually be the set S0, given by the set of vectors beta 0 through beta p in R p plus 1, such that the hyperplane separates the points, but not only that, the norm of beta is non-zero. S should actually be the set S0, since we don't want the norm of beta to be 0. However, we don't have to worry about this if we have at least 2 data points, xi, yi, and xj, yj, in different classes. Okay, if yi is not yj, okay, so that we have 2 different classes, and the norm of beta is 0, then we have that beta 1 through beta p is 0. Okay, since the norm of beta is 0, we get this. But that implies that yi beta 0 is positive and yj beta 0 is positive. Okay, assuming that beta 0, beta 1 through beta p lies in S. Okay. So this this entails that beta 0 is positive and negative. Okay, and that's a contradiction. Okay, so therefore S is a subset of S0, and certainly S0 is a subset of S, so they're actually equal. Okay, so S0 is equal to S. If we find beta 0 star, beta 1 star through beta p star that maximizes the margin, we can use the hyperplane given by beta 0 star plus beta 1 star x1 plus dot 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 plus beta p star xp equals to 0. Okay, we can use this hyperplane to classify a test point x1, x2 through xp. Okay, so here's a test point. We can use this to classify a test point as follows. If this expression is positive, then the test point is assigned to class 1. If this expression is negative, then the test point is assigned to class -1. This way of classifying test points is called the maximal margin classifier. Okay, the maximal margin classifier. Now let's see how the maximal margin hyperplane is found. Letting m sub beta naught beta be given by this, we can reformulate the problem as maximize m sub beta naught beta, where beta naught beta lies in S. Okay, so we're trying to maximize the margin m sub beta naught beta. Here, beta naught comma beta is really beta naught beta 1 through beta p. So I'll just write it like this for short. It turns out that the margin m sub beta naught beta doesn't change if we multiply beta naught and beta by some positive value k. That is, m sub k beta naught k beta is the same as m sub beta naught beta. To see the proof of this, see the optional video or document titled Proof 2. Okay, this fact allows us to impose the following condition. Okay, so the minimum of this, as I ranges from 1 to n, is equal to 1. Okay, so let me write that again. Okay, so this fact allows us to impose this condition here. Okay, to see why, see the optional video or document titled Proof 3. Thus, we can try to find a solution to our maximization problem that satisfies the condition to begin with by imposing the condition here. We now have the optimization problem, maximize m sub beta naught beta, beta naught beta lies in S, given the condition that the minimum of this is 1. Note that m sub beta naught beta equals 1 over the norm of beta times the minimum of this, and that's equal to 1, so we just get 1 over the norm of beta. Okay, so maximizing m sub beta naught beta is the same as minimizing the norm of beta, which is equivalent to minimizing 1/2 the norm of beta squared. So our problem becomes minimize 1/2 the norm of beta squared, where beta naught beta lies in S, given the constraint that the minimum of this is 1. Actually, we can relax the constraint by making it an inequality. So the problem 1, minimize 1/2 the norm of beta squared, given the constraint where the minimum is 1, okay, is equivalent to the problem 2, which is minimize 1/2 the norm of beta squared given the constraint where the minimum is greater than or equal to 1. Okay, so instead of equality, we can replace it with an inequality here. So problems 1 and 2 are equivalent in the sense that the first problem has a solution if and only if the second problem has a solution. Furthermore, the solutions to 1 and 2 will give the same value for m sub beta naught beta. Okay, for the proofs, see the optional videos or documents titled Proofs 4 and 5. We can therefore focus on solving the optimization problem, minimize 1/2 the norm of beta squared, given the constraint where the minimum is greater than or equal to 1. The constraint minimum of this is greater than or equal to 1 is equivalent to the constraint that y sub I times beta 0 plus dot 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 plus beta p xip is greater than or equal to 1 for I ranging from 1 to n. We can reformulate the optimization problem to be minimize 1/2 the norm of beta squared given the constraint where yi times this is greater than or equal to 1 for each of the i's as I ranges from 1 to n. Okay, the requirement that beta naught beta lies in S is unnecessary because the constraint that yi times beta naught plus dot 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 plus beta p xip is greater than or equal to 1 for all of the i's. This implies that yi times beta naught plus dot 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 plus beta p xip is positive. It's greater than 0. Okay, for each of the i's. We can thus reformulate the optimization problem as minimize 1/2 the norm of beta squared, where beta naught beta just lies in R p plus 1. Okay, and the constraint remains this. This is a convex optimization problem where f given by this and gi given by this are differentiable convex functions. Okay, f goes from r p plus 1 to r, and it's defined as 1/2 the norm of beta squared. G sub I goes from r p plus 1 to r, and g sub I is defined as 1 minus y sub I times beta 0 through beta p xip for each I as I ranges from 1 to n. Our convex optimization problem takes the form minimize f of beta 0 through beta p, where beta 0 beta lies in r p plus 1, given the constraint that g sub I of beta 0 through beta p is less than or equal to 0 for I ranging from 1 to n. In this video, we're going to show that scaling the betas by a positive constant k doesn't make a difference to m. Okay, so let's look at the proof. M sub k beta naught k beta is equal to the minimum of this expression. Okay, so here we have k beta, and k beta is everywhere here. Okay, pull that k out. Okay, pull the k out from the norm of k beta. Okay, so they cancel out, and we get just this. But that's just m sub beta naught beta. Okay. So therefore, our claim that m sub k beta naught k beta equals m sub beta naught beta is true. In this video, we're going to show this claim. The problem maximize m sub beta naught beta is equivalent to this problem maximize m sub beta naught beta given the constraint that the minimum of this expression is 1. Okay, so by equivalent, we mean that this problem has a solution if and only if this problem has a solution. Okay, so more specifically, if we have a solution to this problem, then we can scale the betas to get a solution to this constrained problem. Okay, and if we have a solution to this constrained problem, that solution will also be a solution to this unconstrained problem. So let's look at the proof. Okay, suppose beta naught star, beta 1 star through beta p star is an element of S, and suppose that it maximizes m sub beta naught beta. Okay. Then m sub beta naught star beta star is this. Okay. So therefore, solving for the minimum, we get norm of beta star times m sub beta naught star beta star. We can scale our betas by k equals to this to get a solution that has the same maximum m sub beta naught star beta star and satisfies the condition that the minimum is 1. Consider k beta naught star, k beta 1 star, ... k beta p star. Okay. Then m sub k beta naught star k beta star is the same as m sub beta naught star beta star. Okay, this scale k doesn't matter here. Now this element also satisfies the condition given by this. The minimum of this expression is 1. Okay, let's show that. Okay, the minimum, if we plug in k beta naught star through k beta p star here, we get this. But we could factor that k out to get this. And this part is the norm of beta star times m sub beta naught star beta star. And k is equal to this. So they cancel out. And we get 1. Now suppose beta naught plus beta plus lies in S is a solution to this problem, the problem with the constraint. We'll show that beta naught plus beta plus is a solution to the unconstrained problem. Okay, we need to show that m sub beta naught plus beta plus is greater than or equal to m sub beta naught beta for every beta naught beta in S. Let beta naught beta lie in S, and let k be this. Then k beta naught k beta satisfies this constraint, and therefore m sub beta naught plus beta plus is greater than or equal to m sub k beta naught k beta, because beta naught plus beta plus is a solution to the constrained problem. but m sub k beta naught k beta is the same as just m sub beta naught beta because that scale doesn't matter. Okay, and that's this here is what we want it to show. This video we're going to show the following claim. Consider this problem, minimize 1/2 the norm of beta squared, given the constraint that the minimum is 1. Okay, let's call this problem 1. Okay, problem 1 is equivalent to problem 2, given by this, where the constraint is relaxed. So the minimum is greater than or equal to 1 instead of being equal to 1. Okay, first we're going to show that if we assume that problem 2 has a solution, then problem 1 has a solution. And then we'll show that if problem 1 has a solution, then problem 2 has a solution. Okay, we're going to start with assuming that problem 2 has a solution, and then we're going to scale that solution to get a solution to problem 1. Suppose beta naught plus beta plus lies in S is a solution to 2. Let k be 1 over m sub beta naught plus beta plus times the norm of beta plus. Then the minimum of this expression with k beta naught plus through k beta p plus plugged in is equal to this, where we pull the k out. And k is equal to this, and this part is equal to this. So they cancel out, and we get 1. Okay, now let beta naught beta lie in S such that the minimum is equal to 1. Then the minimum is greater than or equal to 1, since it's equal to 1. And so 1/2 the norm of beta plus squared is less than or equal to 1/2 the norm of beta squared, because beta naught plus beta plus is a solution to 1. Okay, 1/2 the norm of k beta plus squared is equal to this, pulling the k out, and then rewriting k as this, 1 over m times the norm of beta plus. Okay, we square that. We get some cancellation, so we get 1 over m squared here. Okay, now by definition, m is equal to this, and if we square it, we get this. Okay, so now we have beta plus, the norm of beta plus squared in the numerator, and keep the minimum squared down here. And that's less than or equal to 1/2 the norm of beta plus squared, because the minimum with beta naught plus through beta p plus plugged in is greater than or equal to 1. Okay, so 1 over that will be less than or equal to 1, and then when you square it, it's still less than or equal to 1. And 1/2 the norm of beta plus squared is less than or equal to 1/2 the norm of beta squared. We already showed this earlier. Okay, so we just showed that 1/2 the norm of k beta plus squared is less than or equal to 1/2 the norm of beta squared. Okay, so k beta naught plus k beta plus is a solution to 1. We just showed that if problem 2 has a solution, then problem 1 has a solution. More specifically, if problem 2 has a solution, we can scale that solution to get a solution to problem 1. Now we're going to show that if problem 1 has a solution, then problem 2 has a solution. Suppose beta naught star beta star in S is a solution to 1. Let beta naught beta in S be such that the minimum is greater than or equal to 1. Let k be 1 over m times the norm of beta. Then the minimum of this expression with k beta naught through k beta p plugged in is equal to k times the minimum of this. And k is equal to this, and this minimum is equal to m times the norm of beta. So they cancel out. And we get 1. So 1/2 the norm of beta star squared is less than or equal to 1/2 the norm of k beta squared. Because beta naught star beta star is a solution to 1. Okay, now 1/2 the norm of k beta squared is equal to 1/2 k squared norm of beta squared. Okay, rewrite k as this, 1 over m times the norm of beta. We get some cancellation, so it's 1 over m squared here. And m is equal to 1 over the norm of beta times the minimum of this expression. So if we square it, we get this. Okay, bring the norm of beta squared to the numerator. Keep the minimum in the denominator. And this right here is less than or equal to 1/2 the norm of beta squared, because beta naught beta satisfies the minimum being greater than or equal to 1. So 1 over the minimum is less than or equal to 1. And then when we square that, we get something that's less than or equal to 1. So 1 over the minimum squared is less than or equal to 1. So that's why we get this. Okay, so 1/2 the norm of beta star squared is less than or equal to 1/2 the norm of k beta squared. And that's less than or equal to 1/2 the norm of beta squared. So therefore, 1/2 the norm of beta star squared is less than or equal to 1/2 the norm of beta squared. So therefore, beta naught star beta star is a solution to 2. In this video, we're going to show that the solutions to problems 1 and 2 give the same maximum values. Okay, so let's look at the proof. Suppose beta naught plus beta plus in S is a solution to problem 2, and beta naught star beta star in S is a solution to problem 1. Then 1/2 the norm of beta plus squared is less than or equal to 1/2 the norm of beta star squared, because beta naught star beta star satisfies the constraint where the minimum is 1, and hence the constraint where the minimum is greater than or equal to 1. And beta naught plus beta plus minimizes 1/2 the norm of beta squared over all such beta naught beta. Okay, so that's why we have this. That implies that the norm of beta plus is less than or equal to the norm of beta star. Okay, but the norm of beta star is 1 over m of beta naught star beta star. Okay. However, m sub beta naught plus beta plus is 1 over the norm of beta plus times the minimum of this. And that's bigger than 1 over the norm of beta plus, because the minimum here is greater than or equal to 1. So the norm of beta plus is bigger than or equal to 1 over m sub beta naught plus beta plus. It follows that 1 over m sub beta naught plus beta plus is less than or equal to the norm of beta plus, which is less than or equal to 1 over m sub beta naught star beta star. Okay, so if we flip this around, we'll get m sub beta naught star beta star is less than or equal to m sub beta naught plus beta plus. Note that beta naught star beta star is a solution to 1, and hence a solution to the problem maximize m sub beta naught beta given that the minimum is 1. Okay, because since you're minimizing the norm of beta in problem 1, you're maximizing the margin. Okay. We showed earlier that a solution to this problem with the constraint is also a solution to the original maximization problem where you just maximize m with no constraint. Okay. So beta naught star beta star is a solution to this problem without the constraint. Therefore, m sub beta naught star beta star is bigger than or equal to m sub beta naught beta for any beta naught beta in S. In particular, it's true for beta naught plus beta plus. So we get this. Now, m sub beta naught star beta star is less than or equal to m sub beta naught plus beta plus, which is less than or equal to m sub beta naught star beta star. Since this is sandwiched in between m sub beta naught star beta star, it's equal to m sub beta naught star beta star. So we get this. Thus, the solutions to 1 and 2 give the same maximum values. Our convex optimization problem is given by this: minimize f of beta 0 through beta p, given the constraint g sub I of beta 0 through beta p is less than or equal to 0 for each I from 1 to n, where f is given by this and gi is given by this. We can solve this using Lagrange multipliers. Consider the Lagrangian L from Rp plus 1 cross Rn to R, given by this: L of x alpha is f of x plus the sum of alpha I gi of x, I ranging from 1 to n. The alpha i's are constant, and they're called Lagrange multipliers. Our convex optimization problem has a solution x star equals b0 star to bp star if there are Lagrange multipliers alpha 1 star to alpha n star such that the following conditions hold. First, g sub I at x star is less than or equal to 0 for all I between 1 and n. This is called primal feasibility. 2. The gradient with respect to x of the Lagrangian L at x star alpha star is 0, where alpha star is alpha 1 star to alpha n star. This is called Lagrangian stationarity. 3. Alpha I star is greater than or equal to 0 for I equals 1 to n. This is called dual feasibility. 4. Alpha I star times gi at x star is 0 for I equals 1 to n. This is called complementary slackness. These conditions are called the KKT conditions. Consider the problem of finding the minimum over x of the maximum over alpha, where alpha I is greater than or equal to 0 for all I, of L of x alpha. This is called the primal problem. Consider also the problem of finding the maximum over alpha, where alpha I is greater than or equal to 0 for all I, of the minimum over x of L of x alpha. This is called the dual problem. It turns out that the minimum of the maximum is the maximum of the minimum if a condition called Slater's condition holds. Slater's condition requires that there is an x in Rp plus 1 such that gi of x is strictly less than 0 for I equals 1 to n. The equality where the minimum of the maximum of L is the maximum of the minimum of L is called strong duality. It also turns out that a solution to our original convex optimization problem is given by a solution to the primal problem. By strong duality, we have that the minimum of the maximum of L is the maximum of the minimum of L. So we can find a solution to our convex optimization problem by solving the dual problem. That is, we want to find the maximum over alpha, where alpha I is greater than or equal to 0 for all I, of the minimum over x of L of x alpha. We start by minimizing L of x alpha. To minimize L of x alpha, set the gradient of L to 0. Okay, L of x alpha is given by this, 1/2 the norm of beta squared plus the sum of alpha I gi of x. Okay, now plugging in what we have for gi of x, we get this. And swapping these two terms around, we pull the negative out and we get this. Okay, taking the partial derivative of L with respect to beta j, we get this here for j ranging from 1 to n. If we take the partial of L with respect to beta 0, we get this. Setting the partial derivative of L with respect to beta j to be 0, we get that beta j is equal to this sum. So the vector consisting of beta 1 to beta p is this sum, the sum of alpha I, yi, xi, I ranging from 1 to n. Similarly, setting the partial derivative of L with respect to beta 0 to 0, we get the sum of alpha I, yi equals 0. Substituting these values for beta into L of x alpha, we get this. Okay, so let's call it L sub d of x alpha. This is called the dual Lagrangian. Now, we want to find the maximum over alpha of the dual Lagrangian L sub d of x alpha. Our problem now is to maximize this expression given the constraints alpha I greater than or equal to 0 for all I, and the sum of alpha I, yi equals 0. Once this new convex optimization problem is solved for alpha, we can find beta from the equation beta equals the sum of alpha I, yi, xi. We can find beta 0 from the complementary slackness condition alpha I times gi of x equals 0 for all I, given by alpha I times this expression equals 0 for all I. That if alpha sub I is greater than 0, then 1 minus yi times beta 0 plus dot 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 plus beta p xip is 0. So that means that this expression is equal to 1. Okay. And in this case, xi is called a support vector. If yi times beta 0 plus dot 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 plus beta p xip is bigger than 1, then alpha I is 0. And xi is not relevant in this linear combination. Okay, so alpha I here will be 0 for that xi. Beta is a linear combination of only the support vectors. If we let f hat of x equal beta 0 star plus beta 1 star x1 plus dot 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 plus beta p star xp, where x equals x1 through xp is arbitrary in Rp, and beta 0 star to beta p star is the solution to our optimization problem, note that we can rewrite f hat of x as this. Okay, x transpose beta star plus beta 0 star, or equivalently, the dot product between x and beta star plus beta 0 star. Okay, this dot product here, it's also called the inner product, although an inner product is more general than the dot product. Since beta star equals the linear combination alpha I, yi, xi, we have that the dot product between x and beta star is the dot product between x and this linear combination, which is the linear combination of the dot products. So here we take x, the dot product between x and xi here, and we pull these constants out. So we can write f hat of x as this here, and any test point x is classified according to the sign of f hat of x. Let's do an example. Suppose we have the following data points, x1, x2, and x3 with y1 equals -1, y2 equals 1, and y3 equals 1. Find the maximal margin hyperplane and identify any support vectors. Our convex optimization problem takes the form minimize f of beta 0, beta 1, beta 2, where beta 0, beta lies in R3. Given the constraint g sub I of beta 0, beta 1, beta 2 is less than or equal to 0 for I equals 1, 2, and 3, where f of beta 0, beta 1, beta 2 is 1/2 the norm of beta squared, and g sub I of beta 0, beta 1, beta 2 is this expression here, and I equals 1, 2, and 3. So g sub 1 equals to this. Okay, if we plug in the values for our data points, g sub 2 is this, and g sub 3 is this. The dual Lagrangian is given by this formula. Okay, so if we plug in the values that we have for our data, we get this. Okay. We want to maximize L sub d subject to the constraints alpha I is greater than or equal to 0 for all I, and alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3 equals 0. That is, we need that alpha I is greater than or equal to 0 for all I, and negative alpha 1 plus alpha 2 plus alpha 3 equals 0. Using alpha 1 equals alpha 2 plus alpha 3, rewrite L sub d as this. Okay, just plug in alpha 2 plus alpha 3 for alpha 1. Simplifying, we get this. So we want to maximize L sub d subject to the constraints alpha 2 is greater than or equal to 0 and alpha 3 is greater than or equal to 0. So we're maximizing L sub d on the positive orthant, alpha 2 greater than or equal to 0 and alpha 3 is greater than or equal to 0. So here's the positive orthant. It's just this quadrant here. Now let's look for any critical points in the interior of the positive orthant by setting the gradient of L sub d equal to 0. Okay, taking the partial derivatives, the partial of L sub d with respect to alpha 2 is this. The partial of L sub d with respect to alpha 3 is this. Setting the gradient equal to 0, we get this system of equations. Okay, solving this, we get alpha 2 is 2/9 and alpha 3 is 2/9. So 2/9 is a critical point in the interior of the positive orthant. L sub d evaluated there is 4/9. Using the second derivative test, we can show that L sub d of alpha has a local max at 2/9. However, a local max of a concave function on a convex set is a global max. L sub d of alpha 2 alpha 3 is a concave function, and the positive orthant E, given by this, is convex. Note also that L sub d of alpha 1 alpha 2 alpha 3 Okay, note that this is also concave. Okay, so what we have here is that L sub d of alpha 2 alpha 3 is a concave function and E is convex. So L sub d of alpha 2 alpha 3 has a global max on E. L sub d of alpha 1 alpha 2 alpha 3 has a global max at alpha 1 alpha 2 alpha 3 over the set F given by this, if and only if L sub d of alpha 2 alpha 3 has a global max at alpha 2 alpha 3 over the set E. It follows that L sub d of alpha 1 alpha 2 alpha 3 has a global max at 4/9, 2/9, 2/9. Okay, so let me write that here. Okay, L sub d of alpha 1 alpha 2 alpha 3 has a global max at 4/9, 2/9, 2/9. Okay, here we just found alpha 1 because we already know alpha 2 and alpha 3. Okay, beta is given by this formula, so plugging in our values for y sub I, xi, and alpha I, we get this. Simplifying, we get this. So beta 1 is 2/3 and beta 2 is negative 2/3. By complementary slackness, alpha I times this expression is 0 for all I. Okay, so for I equals to 1, we get this. Okay, and solving for beta 0, we get 1/3. Okay, so beta 0 is 1/3, beta 1 is 2/3, and beta 2 is negative 2/3. Our hyperplane is given by beta 0 plus beta 1 x1 plus beta 2 x2 equals 0. Plugging in our values for beta 0, beta 1, and beta 2, we get this. Okay, solving for x2, we get this. Okay, so this is the equation of a line. Let's see the graph of this. Okay, so this purple line here. Okay, we have our data points, x1, x2, and x3. As you can see, this purple line separates the two classes. This line is the maximal margin hyperplane. Since alpha 1, alpha 2, and alpha 3 are all non-zero, we have that each xi satisfies this equation. Hence, x1, x2, and x3 all lie on the margin and are therefore support vectors. You can see that from the graph. Okay, imagine that we draw the edges of this slab. x1, x2, and x3, they all lie on the edges of this slab. Okay, let's do a second example. Suppose we have the following data points, x1, x2, and x3, with y1, -1, and y2 and y3 are both 1. find the maximal margin hyperplane and identify any support vectors. Our convex optimization problem takes the form minimize f of beta 0, beta 1, beta 2, where beta 0, beta lies in R3, given the constraint g sub I of beta 0, beta 1, beta 2 is less than or equal to 0 for I equals 1, 2, and 3, where f of beta 0, beta 1, beta 2 is 1/2 the norm of beta squared, and gi is given by 1 minus yi times beta 0 plus beta 1 xi1 plus beta 2 xi2 for each I equals 1, 2, and 3. So G1 is given by this. If we plug in the values for our data. Okay. And similarly, G2 is this and G3 is this. The dual Lagrangian is given by L sub D of X alpha is this. This is the formula for the dual Lagrangian. Okay, so if we plug in the values for our data, we will get this here. Okay. Okay, we want to maximize L sub D subject to the constraints alpha I being greater than or equal to 0 for all I, and alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3 equals 0. That is, we need alpha I greater than or equal to 0 for all I, and negative alpha 1 plus alpha 2 plus alpha 3 equals 0. Okay, I just plugged in the values for the y's. Now, using alpha 1 equals alpha 2 plus alpha 3, rewrite L sub D as follows. Okay, I just plugged in alpha 2 plus alpha 3 for alpha 1. Now, simplifying, we get L sub D equals to this. Okay, so it's just in terms of alpha 2 and alpha 3. So we want to maximize L sub D subject to the constraints where alpha 2 and alpha 3 are greater than or equal to 0. So we're maximizing L sub D on the positive orthant, alpha 2 greater than or equal to 0, and alpha 3 greater than or equal to 0. So it's just this quadrant here in the plane. Let's look for any critical points in the interior of the positive orthant by setting the gradient of L sub D equals to 0. Okay, the partial of L sub D with respect to alpha 2 is this. The partial of L sub D with respect to alpha 3 is this. Okay, so setting the gradient of L sub D to be 0, okay, we get this set of equations. Okay, but we get a contradiction. So this system of equations has no solution. Okay, so there is no critical point in the interior of the positive orthant, alpha 2 and alpha 3 being greater than or equal to 0. We need to check the boundaries where alpha 2 is 0 and alpha 3 is 0. Okay, so that's this line here and this line here. Okay, so the boundary of this quadrant. Okay, so on alpha sub 2 equals to 0, L sub d has a local max at alpha 3 equals to 1/10 relative to the boundary alpha 2 equals 0 and alpha 3 greater than or equal to 0. Okay, the value of L sub d at 0, 1/10 is 1/10. On alpha 3 equals to 0, L sub d has a local max at alpha 2 equals to 2/5 relative to the boundary alpha 3 equals 0 and alpha 2 greater than or equal to 0. The value of L sub d at 2/5 0 is 2/5, which is bigger than 1/10. Since every global max is a local max, the global max has to occur at a critical point relative to a portion of the boundary. Since the local max at 2/5 0 is greater than the local max at 0, 1/10, the candidate for the global max is 2/5 0. In fact, we can show that for a fixed alpha sub 3, the local max value relative to the line L sub alpha 3, given by the set of all pairs alpha 2, alpha 3, where alpha 2 is greater than or equal to 0. So the local max value relative to that line decreases as alpha 3 increases. Okay, therefore there is a global max at 2/5, 0. L sub d of alpha 2, alpha 3 has a global max at alpha 2, alpha 3 over the positive orthant if and only if L sub d of alpha 1, alpha 2, alpha 3 has a global max at alpha 1, alpha 2, alpha 3 over the set of all vectors alpha 1, alpha 2, alpha 3, where alpha 1 is alpha 2 plus alpha 3, and alpha 2 and alpha 3 are both greater than or equal to 0. So it follows that L sub d of alpha 1, alpha 2, alpha 3 has a global max at 2/5, 2/5, 0. Okay, so here we just solve for alpha 1 as 2/5. Okay, since we already know what alpha 2 and alpha 3 are. Okay, now beta is given by this. So if we plug in the values for xi and yi and alpha I, we'll get this vector here. So beta 1 is 2/5 and beta 2 is negative 4/5. By complementary slackness, alpha I times this expression is 0 for all I. Okay, so this holds for, in particular, this holds for I equals to 1. Okay, so for I equals to 1, if I plug in all the values, I get this. Solving for beta 0, I get 1. Okay, so beta 0 is 1, beta 1 is 2/5, and beta 2 is negative 4/5. Our hyperplane is given by this formula here. So plugging in the values for beta 0, beta 1, and beta 2, we get this. Okay, solve for x2, and we get this equation. Okay, now let's take a look at the graph of this line here. Okay, it's this purple line. Here's the data points, x1, x2, and x3, and our line here separates the two classes. Okay, so this is our maximal margin hyperplane. Since alpha 1 and alpha 2 are non-zero, we have that x1 and x2 satisfy this equation. Let me write that here. Okay, so x1 and x2 satisfy this equation, hence x1 and x2 lie on the margin and are therefore support vectors. Okay, you can imagine here, if we draw a line here and here, okay, forming a slab, x1 and x2 lie right on the edges. Let's summarize what we learned in this section. If the xi's of our data are separable by a hyperplane, we want to find the separating hyperplane that has maximal margin. Once we find the maximal margin hyperplane, we can classify new points depending on which side of the hyperplane the new point lies on. In trying to find the maximal margin hyperplane, we end up with a convex optimization problem, which is solved using Lagrange multipliers. We have seen how the maximal margin hyperplane can be found when the xi's are separable by a hyperplane. If the xi's are not separable by a hyperplane, we can still try to find a hyperplane that separates most of the points, but that may have some points that lie inside the margin or lie on the wrong side of the hyperplane. Here's what such a scenario might look like. Okay, so here you can see that one of the orange x's is on the wrong side of the hyperplane. And this one here it's on the correct side, but it's inside the margin. Okay, and this one is on the edge of the margin. The method we will look at is called the support vector classifier, also called the soft margin classifier, because the margin can be penetrated by points from either side. Just as in the case of the maximal margin classifier, we want our hyperplane to be as far as possible from each point that's on the correct side of the hyperplane. So points on the margin or outside the margin but on the correct side of the hyperplane will be as far as possible from the hyperplane. Points inside the margin but on the correct side of the hyperplane will be as far as possible from the hyperplane and as close as possible to the margin boundary. For those points on the wrong side of the hyperplane, we want those points to be as close to the hyperplane as possible. Let's take a look at this graph. Okay, so here I labeled one of the points x1. x1 is on the margin, but it's on the correct side of the hyperplane. Okay, x2 is outside the margin, but on the correct side of the hyperplane. x3 here is inside the margin, but on the correct side of the hyperplane. And x4 is on the wrong side of the hyperplane. Okay, let's make all of this more precise. In the discussion of the maximal margin classifier, we've seen that the perpendicular distance between xi and the hyperplane beta naught plus beta 1 x1 plus dot 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 plus beta p xp equals to 0 is given by this expression here. So 1 over the norm of beta times this if this expression is positive, and negative this if this expression is negative. So the signed perpendicular distance between xi and the hyperplane is given by 1 over the norm of beta times y sub I times beta naught plus beta 1 xi1 plus dot 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 plus beta p xip. Okay, this expression is positive if xi is on the correct side of the hyperplane. It's negative if xi is on the wrong side of the hyperplane. In order to characterize each point x sub I, we introduce variables epsilon sub I, called slack variables, for each xi, where I ranges from 1 to n. If xi is on the correct side of the hyperplane, but inside the margin, like this, then xi protrudes into the margin by a certain fraction of m. So epsilon sub I is the fraction, and it's between 0 and 1. The distance between xi and the hyperplane is given by this distance here, which is m, minus this distance, epsilon sub I times m. Okay, so let me write that here. M minus epsilon sub I m. Factoring the m out, we get this. However, the distance between xi and the hyperplane is given by this. So that's equal to m times 1 minus epsilon I. Solving for m, we get this here. If xi is on the correct side of the hyperplane, but on or outside the margin, then xi does not protrude into the margin by any amount. So here xi is on the margin here, and this xi is outside the margin. Okay, in this case, epsilon sub I is 0. The distance between xi and the hyperplane is this. Okay. And the distance between xi and the hyperplane is greater than or equal to m. As you can see here, the distance between xi and the hyperplane is either equal to m here, or it's greater than m. Okay, so this expression is greater than or equal to m. We can rewrite this as 1 over the norm beta times yi times this times 1 over 1 minus epsilon I is greater than or equal to m. Okay, because epsilon sub I is just 0. Okay, so this is the same as this. xi is on the wrong side of the hyperplane, then xi protrudes into the margin by a certain multiple of m, epsilon sub I times m, where epsilon sub I is greater than 1. Okay, so here's epsilon I times m, some multiple of m, which is greater than 1. So epsilon I is greater than 1. Okay. Now, the distance between xi and the hyperplane is given by epsilon im, okay, minus this distance here, which is m. So let me write that. Okay, so the signed distance is therefore m minus epsilon I times m. However, the signed distance between xi and the hyperplane is given by this formula here. Okay, so that's equal to m minus epsilon I m. Okay, solving for m, we get this times 1 over 1 minus epsilon I. Just as in the case of the maximal margin classifier, we want to maximize the margin so that points on the correct side of the hyperplane are as far as possible from the hyperplane. Not only do we want to maximize the margin, we also want to minimize the violations of the margin, those xi such that epsilon sub I is greater than 0. Imagine that the sum of the epsilon sub i's is less than or equal to k, where k is some constant called the tuning parameter. Since epsilon I being greater than 1 corresponds to points on the wrong side of the hyperplane, we have that the sum of the epsilon sub i's, where I is such that epsilon I is bigger than 1, is greater than or equal to the sum of 1's, ranging over the same i's, and that's equal to the number of points on the wrong side of the hyperplane. So the number of points on the wrong side of the hyperplane is less than or equal to the sum of the epsilon i's, where I is such that epsilon I is bigger than 1, and that's less than or equal to the sum of all of the epsilon i's, and that's less than or equal to k. We're assuming this here. Okay, so the number of points on the wrong side of the hyperplane is bounded by k. The lower the value for k, the less leeway we have for points to violate the margin. Recall that in trying to find the maximal margin hyperplane, we needed to solve the optimization problem, minimize 1/2 the norm of beta squared, given the constraint like this. In trying to find the soft margin hyperplane, we not only want to maximize the margin, but we also want to minimize the violations of the margin. So we need to solve the optimization problem like this. Okay, so we're minimizing 1/2 the norm of beta squared, but we're also minimizing c times the sum of epsilon sub I, where c is some constant, also called a tuning parameter. Okay, and we have the constraint, this expression is greater than or equal to 1 minus epsilon sub I for each I, and epsilon sub I is greater than or equal to 0 for each I. Now here, let's consider the meaning of this constant c. Okay, now remember for the constant k, the other tuning parameter, we said that if we decrease k, then we decrease the leeway for violations of the margin. Okay, but c has the opposite meaning. So if we increase c, then we decrease the leeway for violations of the margin. Okay, and if we decrease c, we increase the leeway for violations of the margin. Once we find a solution to the minimization problem, we can use the hyperplane given by this to classify a test point x1 through xp as follows. If this expression is positive, then the test point is assigned to class 1. If this expression is negative, then the test point is assigned to class -1. This way of classifying test points is called the support vector classifier, or soft margin classifier. Now let's return to our minimization problem. Okay, it's given by this. Minimize 1/2 the norm of beta squared plus c times the sum of the epsilon sub i's. Given the constraint that this expression is greater than or equal to 1 minus epsilon I for each I, and epsilon I is greater than or equal to 0 for each I. This is a convex optimization problem where f, gi, and hi are given as follows. Okay, f, gi, and hi are differentiable convex functions. F is given by 1/2 the norm of beta squared plus c times the sum of the epsilon i's. G sub I is defined to be 1 minus epsilon I minus y sub I times beta naught plus dot 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 plus beta p xip for each I. And h sub I is defined to be negative epsilon sub I for each I. Our convex optimization problem takes the form minimize f, okay, f of beta naught through beta p epsilon 1 through epsilon n, given the constraint where g sub I is less than or equal to 0 for each I, and h sub I is less than or equal to 0 for each I. We can solve this convex optimization problem using Lagrange multipliers. Consider the Lagrangian L from Rp plus 1 plus n cross Rn cross Rn to R, given by this. X consists of beta naught, beta 1 through beta p. Alpha consists of alpha 1 through alpha n. And mu consists of mu 1 through mu n. Okay, alpha I and mu I here are called Lagrange multipliers. L of x alpha mu is given by this. If we plug in what we had for f, gi, and hi. Okay. Now here, we can pull a negative sign out to get this here. Okay, and we can pull this negative from negative epsilon sub I, pull it out to get this here. Okay. Now we want to minimize L of x alpha mu. Let's find the gradient of L with respect to x and set it equal to 0. The partial derivative of L with respect to beta j is given by this for j equals 1 through n. The partial of L with respect to beta naught is this. And if we take the partial derivative with respect to epsilon sub j, then we get this for j equals 1 to n. Setting the partial derivative of L with respect to beta j equals to 0, we get that beta j equals to this. So the vector consisting of beta 1 through beta p is this. And so beta is equal to that linear combination. Setting the partial derivative of L with respect to beta not equals to 0, we get that this sum is equal to 0. Setting the partial of L with respect to epsilon sub j equals to 0, we get alpha I is c minus mu I for I equals 1 through n. Primal feasibility requires that g sub I of x is less than or equal to 0 for all I, and h sub I of x is less than or equal to 0 for all I. In other words, this expression is greater than or equal to 1 minus epsilon I for all I, and epsilon I is greater than or equal to 0 for all I. Dual feasibility requires that alpha I and mu I are greater than or equal to 0 for all I. Substituting the values for beta and alpha I into L, we get L sub d given by this. Okay, after simplifying, we should get this. This is called the dual Lagrangian. Now, we want to find the maximum of the dual Lagrangian over alpha and mu, where alpha I and mu I are greater than or equal to 0 for all I. Our problem now is to maximize the dual Lagrangian over alpha mu, given the constraints alpha I is greater than or equal to 0 for all I, mu I is greater than or equal to 0 for all I, the sum of the alpha I yi is 0, and alpha I equals c minus mu I for all I. And that problem is the same as maximizing the dual Lagrangian over alpha mu given the constraints where alpha I is between 0 and c for all I. This linear combination is 0, and alpha I is c minus mu I for all I. Since the function being maximized does not depend on mu, the problem is equivalent to maximize the dual Lagrangian over just alpha, given the constraints where alpha I is between 0 and c for all I, and this linear combination is 0. Once this new convex optimization problem is solved for alpha, we can find beta. We can find beta from this equation here. By the complementary slackness condition, alpha I gi is 0 for all I, and mu I hi is 0 for all I. That is, alpha I times this expression is 0 for all I, and mu I times epsilon I is 0 for all I. If alpha I is 0, then mu I is c because alpha I is c minus mu I. And so from here, we get that epsilon I is 0 because mu I times epsilon I is 0. If alpha I is greater than 0 and epsilon I is 0 for some I, then we can find beta naught from this equation here. Okay, we would have that alpha I is greater than 0, so that goes away. And then epsilon I here would be 0. We have yi and we have beta 1 through beta p, and we have xi1 through xip. So we have beta 0 here, we can just solve for that. The non-zero epsilon I can be found from the equations given by alpha I times this expression equals 0 for all I. If we let f hat of x be given by beta naught star plus beta 1 star x1 plus dot 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 plus beta p star xp, where x equals to x1 through xp is an arbitrary element in Rp, and beta naught star through beta p star is the solution to our optimization problem, then f hat of x is equal to the dot product between x and beta star plus beta naught star. Okay, so f hat of x is equal to beta naught star plus this part, which is just the dot product between x and beta star. Now, since beta star is a linear combination like this, and we're taking the dot product here between x and beta star, we get a linear combination of dot products. So it's x dot xi, and alpha I, yi are just the coefficients. Okay, so f hat of x can be written like this. Any test point x can be classified according to the sign of f hat of x. Note that if alpha I is greater than 0, then this expression is equal to 0. So yi times beta naught plus dot 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 plus beta p xip is equal to 1 minus epsilon I. And xi is called a support vector. If yi times beta naught plus dot 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 plus beta p xip is strictly bigger than 1 minus epsilon I, then 1 minus epsilon I minus this expression will be less than 0. So that means that alpha I is 0 because alpha I times this is equal to 0. Okay, and this here would be negative. So alpha I would be 0. And in this case, xi is not relevant in the linear combination for beta, because if alpha I is 0, then this part will be 0 and xi doesn't really count. Okay, beta is a linear combination of only the support vectors. Okay, let's do an example. Suppose we have the following data points, x1, x2, x3, and x4, with y1 and y2 equal to 1, and y3 and y4 equal to -1. Find the soft margin hyperplane with c equals to 2, and identify any support vectors. Our convex optimization problem takes the form minimize f, where beta naught beta epsilon lies in R7, given the constraint where g sub I is less than or equal to 0 for I equals 1 through 4, and h sub I is less than or equal to 0 for I equals 1 through 4, where f is given by this, and gi is this expression for each I equals 1 through 4, and h sub I is negative epsilon sub I for I equals 1 through 4. So G1 through G4 are given by this, and H1 through H4 are given by this. The dual Lagrangian is given by this formula. So if we plug in the values that we have for xi and the alpha i's, we get this. We want to maximize L sub d of alpha, subject to the constraints alpha I being greater than or equal to 0 and less than or equal to c for all I, and alpha 1 y1 plus alpha 2 y2 plus alpha 3 y3 plus alpha 4 y4 equals 0. That is, we need alpha I between 0 and c for all I, and alpha 1 plus alpha 2 minus alpha 3 minus alpha 4 equals 0. These constraints give us a four-dimensional plane in the positive box alpha I between 0 and c for all I. Using alpha 1 equals negative alpha 2 plus alpha 3 plus alpha 4, rewrite L sub d as this. Okay, so L sub d is now just a function of alpha 2, alpha 3, and alpha 4. The constraints alpha I being between 0 and c for all I, and alpha 1 equals to negative alpha 2 plus alpha 3 plus alpha 4. These constraints give us a solid region inside the positive box alpha 2, alpha 3, alpha 4 greater than or equal to 0 and less than or equal to c. Alpha 1 being between 0 and c implies that this expression is between 0 and c. Solving for alpha 4, we get that alpha 4 is greater than or equal to this, and that's a plane, and it's less than or equal to c plus alpha 2 minus alpha 3, and that's another plane. So alpha 4 is between this plane and this plane. Okay, let S be the solid defined by the set of all three tuples, alpha 2, alpha 3, alpha 4, where alpha 2, alpha 3, alpha 4 are between 0 and c, and alpha 4 is between these two planes. S looks roughly like this. Okay. So here we have a the positive box, okay, with side length c, and S is just this solid region inside this box. Okay, S is an 8-sided solid inside the positive box. Think of a slanted slab cutting through the positive box. S would be the intersection of the slab and the box. We want to maximize L sub d of alpha 2, alpha 3, alpha 4 on S. L sub d of alpha 2, alpha 3, alpha 4 is a continuous function on the closed and bounded region S. So to find the absolute maximum of L sub d on S, we need to check for any critical points in S and for any extreme values of L sub d on the boundary of S. The largest value of 1, the values of L sub d at any critical points in S, and 2, the extreme values of L sub d on the boundary of S, is the absolute maximum value. Let's look for any critical points in the interior of S by setting the gradient of L sub d equal to 0. So here are the partial derivatives of L sub d. Setting the partial derivatives equal to 0, we get this. And this system has no solution. Okay, so there is no critical point in the interior of S. We need to check the boundary of S. The boundary of S consists of 8 faces. To find the extreme values of L sub d on the faces, we need to check for any critical points inside the faces and for the extreme values on the edges of each face. The calculations are tedious, and it turns out that for c equals to 2, the maximum value of L sub d is 6, and it occurs at alpha 1 through alpha 4 equals 2, 2, 2, and 2. So beta is given by this formula, and therefore beta is 2, 0. By complementary slackness, we have this. This expression equals 0 for all I equals 1 through 4. Okay, this gives us a system of 4 equations and 5 unknowns, epsilon 1 through epsilon 4, and beta naught. Solving this system gives epsilon 1 equals to 2, epsilon 2, 3, and 4 are 0, and beta naught is negative 1. The equation of our hyperplane is given by beta naught plus beta 1 x1 plus beta 2 x2 equals to 0. So plugging in our beta values, we get this. And solving for x1, we get 1/2. Okay, so let's look at the graph. So here's the line, x1 equals to 1/2. And here are the data points, x1, x2, x3, and x4. Okay. Since alpha I is positive for I equals 1 through 4, we get that this equation is true for each I. And therefore, x1, x2, x3, and x4 are all support vectors. Okay, you can see that from the graph. Here, x1, x2, x3, and x4. So they're on the edges of the margin. One last thing. What happens if we increase or decrease c? I repeated the process we just performed to the cases c equals to 1 and c equals to 4. For c equals to 4, L sub d has an absolute maximum value of 10 at alpha 1 through alpha 4 equals 4, 2, 3, and 3. And beta equals 2, 0. Beta naught is negative 1. Epsilon 1 is 2. Epsilon 2, 3, and 4 are 0. And the hyperplane is x1 equals to 1/2. The same result we got for c equals to 2. For c equals to 1, L sub d has an absolute maximum value of 3.5, and it occurs at alpha 1 through alpha 4 equals 1, 1, 1, 1. Okay, beta is 1, 0. The complementary slackness equations given by this give us a system of 4 equations and 5 unknowns: epsilon 1, epsilon 2, epsilon 3, epsilon 4, and beta naught. Okay, and this system has more than one solution. One solution is beta naught equals to 0, epsilon 1 equals to 1, epsilon 2 is 0, epsilon 3 and 4 are both 1. And the hyperplane is x1 equals to 0. If we take a look at the graph, here's x1 equals to 0. And here are the edges of the margin. Here are the data points, x1, x2, x3, x4. Okay. And remember that epsilon 2 is 0. So that's corresponding to x2. Okay, epsilon 2 is 0. And epsilon 1, epsilon 3, and epsilon 4 are both 1. So they protrude into the margin by a factor of 1 times the margin distance. So x1 protrudes into the margin by 1. Factor of 1 here. x3 and x4, they protrude in from this direction by a factor of 1 here and here of the margin distance. Another solution is beta naught equals to -1, epsilon 1 is 2, epsilon 2 is 1, epsilon 3 and 4 are 0. The hyperplane is x1 equals to 1. Okay, let's take a look at the graph. Okay, so here's x1 equals to 1, and here are the edges of the margin. Here are the data points, x1, x2, x3, x4. Okay, notice epsilon 1 is 2, so it protrudes in from this direction by a factor of 2, so 1, 2. Epsilon 2 is 1, so we can see it protrudes into the margin by a factor of 1. Epsilon 3 and 4 are both 0, and they're right on the edges. They're right on the edge of the margin. Notice that in this case, c equals to 1, so we decreased the value of c from c equals to 2. Okay, so since we're decreasing the value of c, we're increasing the leeway for violations of the margin. And you can see that from the graph here. We have a lot more violation of the margin than we have in the case of c equals to 2. Okay, the same thing in this example here. You can see there's a lot more leeway for violating the margin. Let's do another example. Suppose we have the following data points: x1, x2, x3, x4, and x5, with y1, y2, and y3 equals to 1, and y4 and y5 equal to -1. Find the soft margin hyperplane with c equals to 1, and identify any support vectors. Our convex optimization problem takes the form minimize f. Given the constraint, where g sub I is less than or equal to 0 for all I, and h sub I is less than or equal to 0 for all I, where f is given by 1/2 the norm of beta squared plus c times the sum of epsilon I, and g sub I is given by this for each I, and h sub I is equal to negative epsilon I for I equals 1 through 5. So G1 through G5 are given by these expressions if we plug in the values that we have for our data. And H1 through H5 are just negative epsilon I for each I. The dual Lagrangian is given by this formula. So if we plug in the values for our data, we get this. And we want to maximize L sub d of alpha subject to the constraints alpha I is between 0 and c for all I, and alpha 1 y1 plus dot 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 plus alpha y alpha 5 y5 is 0. That is, alpha I is between 0 and c for all I, and alpha 1 plus alpha 2 plus alpha 3 minus alpha 4 minus alpha 5 is 0. These constraints give us a 5-dimensional plane in the positive box, alpha I between 0 and c for all I. Let H be the 5-dimensional plane given by the set of 5 tuples where alpha I is between 0 and c for all I, and alpha 1 plus alpha 2 plus alpha 3 minus alpha 4 minus alpha 5 is 0. We want to maximize L sub d of alpha 1 through alpha 5 on H. To find the maximum of L sub d of alpha 1 through alpha 5 on H, we can use any computational software. It turns out that for c equals to 1, the maximum value of L sub d on H is 7/2, and it occurs at alpha 1 through alpha 5 equals 1, 1/2, 1/2, 1, 1. The formula for beta is given by this, so beta is negative 1, 0. By complementary slackness, we have alpha I times this expression is 0 for all I, and mu I times epsilon I is 0 for all I. Since alpha 2 and alpha 3 are not c, and alpha I is c minus mu I for all I, we have that mu sub 2 and mu sub 3 are not 0. But that implies epsilon 2 and epsilon 3 are 0, since mu I times epsilon I is 0 for all I. Using this equation, we can solve for beta naught and the remaining epsilons. We get beta naught equals to 1, epsilon 1 equals to 1, epsilon 2 is 0, epsilon 3 is 0, epsilon 4 is 2, and epsilon 5 is 0. The equation of our hyperplane is given by beta naught plus beta 1 x1 plus beta 2 x2 equals 0. So we get 1 minus x1 equals 0. Solving for x1, we get x1 equals to 1. Okay, so let's look at the graph. So here's the line x1 equals to 1. And here are the data points, x1, x2, x3, x4, and x5. Since alpha I is positive for I equals 1 to 5, we have that this equation holds for each I. So x1 through x5, they're all support vectors. What happens if we increase or decrease C? If C equals to 2, L sub D has an absolute maximum value of 13.5, and it occurs at alpha 1 through alpha 5 equals 2, 3/4, 3/4, 2, and 3/2. Beta is equal to -1, 0. Beta naught is 1. Epsilon 1 is 1. Epsilon 2 and 3 are 0. Epsilon 4 is 2. And epsilon 5 is 0. And the hyperplane is x1 equals to 1. The same result we got for C equals to 1. For C equals to 1/2, L sub D has an absolute maximum value of 15/8, and it occurs at alpha 1 through alpha 5 equals 1/2, 1/4, 1/4, 1/2, and 1/2. Beta is given by -1/2, 0. Beta naught is 1. Epsilon 1 is 1/2. Epsilon 2 is 0. Epsilon 3 is 0. Epsilon 4 is 2. And epsilon 5 is 1. And the hyperplane is x1 equals to 2. Let's take a look at the graph. So here's x1 equals to 2. And I put the margin edges here and here. So we also have the data points, x1, x2, x3, x4, and x5. So notice epsilon 1 is 1/2, so that corresponds to x1 here, and x1 protrudes into the margin by 1/2 the length of the margin. So here the length of the margin is 2, so 1/2 of 2 is 1, so it protrudes into the margin by 1. Epsilon 2 and 3 are both 0. They're right here on the edge of the margin. Epsilon 4 is 2, so coming from this direction, it protrudes in to the margin by 1, 2. Epsilon 5 protrudes in by a factor of 1 times the margin. Okay, and one last thing, in this case, C equals to 1/2, and we decrease C from 1. So by decreasing C, we're increasing the leeway. So we're allowing more violations to the margin. Let's summarize what we learned in this section. If the xi's are not separable by a hyperplane, we can still try to find a hyperplane that separates most of the points, but that allows some violations of the margin. Once we find the soft margin hyperplane, we can classify new points depending on which side of the hyperplane the new point lies on. To find the soft margin hyperplane, we maximize the margin while penalizing violations of the margin. We end up with a convex optimization problem, which is solved using Lagrange multipliers. So far, we have seen that we can use the maximal margin classifier to separate the two classes of data points when they are linearly separable. We have also seen that even if the data points are not linearly separable, we can still fit a hyperplane that separates most of the points, but that allows violations of the margin. We did this using the support vector classifier. If the data points are not linearly separable and it appears that the decision boundary separating the two classes is nonlinear, we can use what's called the support vector machine or support vector machine classifier. Okay. The idea is to consider a larger feature space with data points in this larger space associated with the original data points, and to apply the support vector classifier to this new set of data points in the larger feature space. This will give us a linear decision boundary in the enlarged feature space, but a nonlinear decision boundary in the original feature space. Let's make this more precise. Suppose x1, y1 through xn, yn are our training data points. Each xi is a p-vector in Rp. So our feature space is Rp. What we want to do is enlarge the feature space Rp by mapping each x in Rp to a vector in Rm, a bigger space. Let h from Rp to Rm be defined by h of x equals this vector h1 of x, h2 of x through hm of x, where h sub I from Rp to R are some functions. Okay, the hi are called basis functions. Now consider the points h of x1, h of x2 through h of xn in Rm. Using the new training set, h of x1, y1 through h of xn, yn, in the new feature space, we can apply the support vector classifier as usual and obtain a hyperplane in Rm that softly separates the points h of x1 through h of xn. Recall that in the process of solving the convex optimization problem for the support vector classifier, the dual Lagrangian was given by this formula. Now, since we're using h of xi and h of xj instead of xi and xj, the dual Lagrangian becomes this. Okay, so here we have h of xi and h of xj instead of just xi and xj. And we can rewrite this as the dot product between h of xi and h of xj. Okay. Solving the convex optimization problem with xi's replaced by h of xi's gives beta j equals to this. Okay, so here we have the linear combination of alpha I yi times the jth component of h of xi for j equals 1 through m. And therefore beta is the sum alpha I yi h of xi. If we let f hat of z be given by beta naught star plus beta 1 star z1 plus dot 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 plus beta m star zm, where z is z1 through zm is arbitrary in Rm, and beta naught star beta 1 star through beta m star is the solution to our optimization problem, then f hat of z can be written like this: the dot product between z and beta star plus beta naught star. Now, since beta star is a linear combination like this of h of xi's, f hat of z can be written like this: a linear combination of the dot products between z and h of xi. Okay, and we have beta naught star here. Okay, so f hat of h of x is equal to this, where we just place h of x in for z. So we plugged in h of x for z, we get this. Okay, so f hat of h of x is equal to this for any x in RP. Okay, any test point x in RP can be classified according to the sign of f hat of h of x. So to classify x in RP, we consider the associated point h of x in Rm and classify h of x using a linear decision boundary. If we look at the solution function f hat of h of x given by this, the dot product between h of x and h of xi is an instance of k of x comma x prime given by the dot product between h of x and h of x prime, what's called a kernel function. Okay, so it takes a pair x prime and gives you the dot product between h of x and h of x prime. A kernel is essentially a function that can be represented as the inner product of the images of the input values under some transformation h. For certain transformations h, the kernel function is efficiently computable. If we have k of x prime expressed in terms of x and x prime, we don't need to know what h looks like. Some examples of kernel functions are polynomial kernels given by k of x prime equals to this, 1 plus the dot product between x and x prime, that whole thing taken to the power n. And radial kernels, okay, k of x prime is given by e to the power negative gamma, some constant, times the square of the norm of x minus x prime. Okay, so here we're just taking the distance between x and x prime and then squaring it here. Okay, note that we can compute these kernels by plugging in values for x and x prime without knowing what the transformation h is. Okay, h doesn't occur here or here. Okay, only x and x prime occur. So as long as we're able to plug in values for x and x prime, we can get these values. Now, instead of constructing a transformation h explicitly and computing the dot products between h of x and h of xi, we can replace the dot products that occur in the dual Lagrangian and the solution function f hat with kernels like so. Okay, so here's the dual Lagrangian, and we put k of xi xj here, okay, instead of the dot product between h of xi and h of xj. And for f hat of x, we put the kernel k of x xi here, okay, instead of the dot product between h of x and h of xi. Okay, so f hat of x is equal to this for any x in RP. Now, this replacement is called the kernel trick. Any test point x in RP can be classified according to the sign of f hat of x. This is how the support vector machine classifies points in RP. The kernel k should be a valid kernel. That is, there should be a feature space mapping H that corresponds to k. By Mercer's theorem, It's sufficient that K be symmetric, positive, semi-definite. In the support vector machine method, the enlarged feature space could be very high dimensional, even infinite dimensional. By working directly with kernels, we don't have to deal with the feature mapping H or the enlarged feature space.